and the state of the science for population estimate. And if you all heard that, this meeting is being recorded, and it will be available in the future on the Delta Stewardship Council website. Another note here, I know that many folks are interested in this workshop, but please don't share the meeting link because we do have a workshop cap at 300. We cannot go over that. So I want to welcome everybody. Obviously, with such a large group, we can't do a round robin and introduce everybody, but I want to point people to the participants list so you can see who is in the virtual room with us together. I see a lot of familiar folks from many different agencies, NGOs, and research institutions. So welcome, everybody. We're going to get this kicked off. So Brandon, would you advance that slide there? Great. Just go ahead and go to the next one. Great. I'm going to just review the objectives of this workshop, and this should be in your materials packet. This is a good time to check out that packet. It is rich with information, and we will be referring to those documents today and tomorrow. So maybe if you haven't opened those, take a moment to get those arrayed on your screen here. The objective of this workshop is to convene subject matter experts in order to explore the best possible approaches to accurately estimating the population of spring-run Chinook salmon in the Sacramento River drainage. The workshop will help to more accurately inform management actions, including requirements described in California's Department of Water Resources incidental take permit as part of the State Water Project operation. Okay, next. So you all have this agenda in your meeting packet, but I do want to just go over what we'll be doing in day one here. First, there'll be a couple sets of opening remarks from Louise Conrad, Deputy Executive Officer from the Delta Stewardship Council, and Carl Wilcox, Policy Advisor to the Director for Delta California Department of Fish and Wildlife. Then we'll have a context-setting presentation from Ted Summer, Lead Scientist with Department of Water Resources, and Brooke Jacobs, an Environmental Program Manager with CDFW. Then we're going to do a little break with a digital collaboration tool called a Mentimeter, and these will be questions that you'll be able to see a little bit more about who's in this virtual room. It's a fun little exercise. For that, I will just warn you, if you could have a web browser open, or you can use your web browser on your smartphone. Either one will work, and we'll go over the instructions for that when the time comes. Then we'll move into some presentations from Rachel Johnson and Flora Cordoliani, and then we'll have questions and answers for those two presentations, and then a break. And then we'll go into presentations from Daphne Gill and Adam Duarte, and then again, question and answer on those. Then we'll have another fun Mentimeter recap and an overview of what's to come in day two with the breakout sessions, so you know what's going to come up. So that's our agenda for today. And again, on the side, you'll see these background documents. Those are included in your packets. And I think those will be really helpful as reference documents as you hear the presentations and for tomorrow's breakout. So I encourage you to open those up. Okay, next. Then to just give you a little preview of what's happening in day two, we're going to just have breakout groups. So there'll be three topics. One is monitoring and gaps, two is run identification tools, and then three is JPE approaches. And you can see on this agenda slide, there are going to be 2 breakout groups per topic. So you can see who your breakout group facilitators are and who your note takers are. And then there's a set of questions, 3 questions, which you'll be addressing. So day 1 is setting you up for the state of science with these presentations. And then day 2 is where much of the input we're hoping to gather from all of the great minds here. Go ahead and advance. In day 3, we will reconvene and we'll hear what happened in those breakout sessions with synthesis presentations from Ted, Summer, and Louise Conrad, and then we'll close. And advance. Brandon, would you just advance one more slide? I just want to do the next steps before we go into housekeeping. No, there we go. So just to close out what the products will be from this workshop, there'll be a video recording of the day 1 of the workshop. So colleagues, maybe your colleagues who couldn't make it for today, you'll be able to share that with them. There will be a summary of the workshop, including those day 2 breakout groups and the synthesis summary from them. So that will be captured. And you can find them at deltacouncil.ca.gov/events once they're up. In the future, there will be a peer-reviewed scientific article that's produced and will be published in the upcoming year. Okay, Brandon, would you go back to those housekeeping slides? Thanks. Just quick housekeeping. I'm sure you all are familiar now. We've been all on webinars for months now, but for this one, it's very large. You will remain on mute throughout the webinar until I call on you to speak during the question and answer and discussion. And then at that point, please feel free to unmute yourself. I will try to use the chat to track who is wanting to speak. Please don't put your whole comment in the chat. Just let me know your name and affiliation and that you have a comment or question, and then I'll get you on deck for the queue. I just want to warn everybody for day 1, the question and answer sessions after each of the presentations are only 15 minutes. So most of the discussion is going to happen in your breakouts tomorrow. And again, if you're experiencing technical difficulties, there are some phone number and of course the email. If everyone could just mute themselves, we just have a little background. There we go. Thanks, Brandon. Brandon is our web team guru. So I might be talking with him throughout the webinar to just manage the workshop. Great, Brandon, will you advance? Okay, so the ground rules for the workshop, just setting them here in the beginning, we're listening and seeking to understand. I encourage everybody to bring curiosity. And then be hard on the problems, not the people, and then be brief. If you would allow me to help people close or allow the facilitators tomorrow in your breakout groups to help tease out the nugget of what you were trying to say. Thanks for your good grace and patience on that. Okay. Let's see. Just checking that I've covered everything with everybody. Again, for those who joined after I started, when you enter the webinar, you are going to be on mute. And then for the discussion, I will call on you and you can unmute yourself. So now I would like to kick us off and introduce for opening remarks Louise Conrad, Deputy Executive Officer, Delta Stewardship Council. Louise.
Good morning, everyone. Julie, can you hear me?
I can. You're loud and clear, and I can see you. So you're on.
Excellent. Thank you. Thank you for that introduction. So my name is Louise Conrad, as Julie already said, and I am introducing this workshop on behalf of the Delta Science Program. Brandon, could you please bring up my title slide? While you're doing that, I want to say it is a pleasure and a real honor to introduce this science workshop on Sacramento River drainage, spring run, Chinook salmon. We are very excited for our discussions over the next few days. I want to just take this few minutes to give a brief overview of our goals for the workshop in a little more depth than Julie already provided an excellent overview of the agenda. And then I also want to thank some of the very hardworking people that have made this possible this week, and then turn it over to Carl Wilcox, Ted Summer, and Brooke Jacobs to highlight the management relevance. Next slide, please, Brandon. So for us at the Delta Science Program, these scientific workshops provide a way for us to achieve our mission of providing the best possible unbiased scientific information to inform decision-making in the Delta. Generally, this is important because we really need these workshops as an opportunity to bring us together to discuss complex issues that really need science support. And we have several goals with these workshops in general. One of them is to develop a shared understanding of the science, because when we have multiple scientists and multiple scientific disciplines giving attention to an issue, it can be hard for even just the scientists to be on the same page. Workshops are our chance to synthesize our knowledge and identify our knowledge gaps. They're also a chance for us to engage people from diverse perspectives, and I think we're going to find this week as a case in point. We have many people here in this virtual workshop that don't otherwise get to interact with each other on a day-to-day basis. And we hope that in doing this, in synthesizing the science and in reaching out and bringing together a community, we develop a foundation of trust. And this foundation of trust is one of the most important ingredients to identifying together clear science actions that we need to really inform management. Next slide, please, Brandon. So this workshop this week is our opportunity in our workshop to identify science and monitoring needs to produce a robust juvenile production estimate, or JPE, that can be used to inform take for water project operations. As Carl Wilcox, Ted Summer, and Brooke Jacobs will highlight, this is a requirement of the incidental take permit for the state water project. To help us at the outset of this workshop all be on the same page as much as possible, a team of scientists have been working with the steering committee to develop what we're calling State of the Science pre-workshop fact sheets. All of you should have received those from us last week. These fact sheets are authored by scientists from the Delta Science Program, NOAA Fisheries, Department of Water Resources, California Department of Fish and Wildlife, and UC Davis. And our purpose in doing this is to come into this workshop.
Speak. How about that? How about let me speak right now?
Our purpose is to come into the workshop as much as possible with a synthesized and common understanding of some of the relevant science with respect to population estimates for spring run Chinook salmon. The themes of these fact sheets: approaches to the development of JPEs, life history, monitoring, and run identification, carry over into the organization for the agenda of the workshop, especially the breakout sessions tomorrow. Next slide, please. So first, finally, I just want to say that the first step to achieving all of these workshop goals at any workshop is to have people show up. We are excited and honored to see the high level of engagement at this workshop. As Julie mentioned, we have over 300 people registered and about 200 people here today together right now. And importantly, you come from an impressive array of affiliations, from academics, scientists, and managers at governmental agencies, nonprofit organizations, and a long list of stakeholders. This means we are off to a great start, so thank you for being here. And then also I want to say a very big special thank you to the organizers and facilitators of this workshop. The agenda development was guided by a steering committee that had representation from the Delta Science Program, Department of Water Resources, California Department of Fish and Wildlife, U.S. Fish and Wildlife Service, the State Water Contractors and Metropolitan Water District, NOAA Fisheries, and the Bureau of Reclamation. Special thanks, very special thanks to Henry DeBay, Eva Bush, and Pascal Gertler of the Delta Science Program for facilitating the planning process, and our external affairs group at the Stewardship Council, particularly Brandon Chapin, who is facilitating this right now, and to Brittany Young for their excellent communication around this workshop, which is our very first virtual one. Planning only started 4 months ago for this effort, and that is not much time to get together high quality fact sheets, an agenda, facilitation support, thank you, Julie, and to have 200 people here right now. So thank you so much. And I can't wait to dive into the science with you. And I will turn it over either back to Julie or to Carl for more opening remarks. Thank you so much.
Thanks, Louise. Thank you, Louise. I will now introduce Carl Wilcox, Policy Advisor to the Director for the Delta, California Department of Fish and Wildlife. Carl?
Thank you, Julie, and thank you, Louise. I'm not going to have a whole lot to add to the very thorough introduction that Louise provided. I think she captured the essence of this effort. I just want to express the department's appreciation to the Delta Science Program for helping to convening this meeting, as well as the steering committee and the science program staff who have obviously put a great deal of effort into organizing this and providing introductory materials. We also appreciate the high level of interest in this issue. Spring Run is kind of the, I don't know, stepchild of Central Valley salmon runs, and is certainly of great importance as it relates to addressing science questions to inform management relative to implementation of the department's incidental take permit for the State Water Project that was issued this spring, as well as an element or a conservation measure identified in the NIF's biological opinion for the long-term operations of the state and federal water projects. So, this workshop's the first step in addressing that issue in the development of a JPE, and certainly is a significant undertaking. This element had a specific timeline set for getting it started, and this is the first step and is very significant in achieving kind of a compliance step. So with that, I don't think I need to elaborate more, and we'll turn it over to Brooke and Ted to get into the specifics and objectives associated with the workshop. But I want to thank everybody for their participation and look forward to the outcomes of this and the ongoing development of the JPE for Spring Run.
Thank you, Carl. Now I will introduce Brooke Jacobs, Environmental Program Manager with California Department of Fish and Wildlife, to start off this presentation on context setting.
All right, can everyone hear me? Julie, yes?
Yes, we can hear you. Yeah, you're good.
Okay, thank you for that introduction. I also very much appreciate everyone's interest in learning and discussing Spring Run Chinook Salmon. Also want to thank the Delta Science Program for their tremendous fast-paced effort to get this workshop launched. It will be a really interesting scientific discussion about Spring Run Chinook Salmon, and also helpful for implementation of the incidental take permit that Carl just mentioned. So I just want to start off by saying I hope that you are all safe and well. These are interesting times. And like I said, I'm very glad to have a chance to gather together virtually to talk about Spring Run Chinook Salmon, even if we can't convene the workshop in person. So I'm just going to provide very brief management context with Ted before we get started and get to hear our excellent presentations for the rest of the morning. So as probably all of you already know, Spring Run Chinook Salmon is listed as threatened under both the California and the Federal Endangered Species Act. And in March 2020, the department issued an incidental take permit to the Department of Water Resources for operations of the State Water Project in the Sassoon Marsh and the Delta. So as a part of this permit, DWR is required to modify operations in the South Delta to minimize entrainment and take of Spring Run based on the presence of hatchery surrogates in the fish salvage facilities in the South Delta. So the permit also requires the Department of Water Resources to develop a new science and monitoring program and an approach to calculating a juvenile production estimate for spring run each year. So this science and monitoring and production estimate element of ITP is important because it will provide a critical tool to help us understand spring run distribution and abundance as they move from the tributaries down through the delta. So after completion of this juvenile production estimate, the Department of Water Resources may request an amendment to the permit to modify their approach to minimizing entrainment and take of spring run by the State Water Project. So this workshop is really the first step in gathering a very wide array of expertise in spring run Chinook salmon biology to start to think through the process of how we better conduct science and monitoring to understand and fill important knowledge gaps for spring run Chinook salmon. And as Carl mentioned earlier, the 2019 biological opinion issued by NIMS also references the importance of assessing delta performance measures for young of year spring run Chinook salmon. So I look forward to hearing the presentations today and the discussion and synthesis in the coming days. And I'll turn it over to Ted now.
Great, thanks, Brooke. And I want to welcome you all on behalf of Department of Water Resources. As you just heard from Brooke, DWR is in the hot seat to develop a population estimate for spring run that can be used for management. Basically, the workshop here is designed as a public scoping meeting to try and inform planning for the monitoring and science that we'll need to develop that population estimate. So as you've heard by some of the previous speakers, the idea is we're going to assess the current state of science and monitoring for spring run and to try and identify some of the key gaps we have in the science and monitoring that we're going to need to develop a population estimate. I want to emphasize that our goal today is not actually to develop a candidate method to develop that population estimate. Instead, we're really here as part of a scoping effort to provide the foundation for the necessary research, development, and monitoring that we will need to develop that JPE. I also want to point out that our focus is on the population estimate and not on a number of other important science and management issues for spring run. There are a lot of other important topics for salmon out there. We won't be covering things like the design of restoration projects, the role of external factors like ocean conditions, climate change, harvest, many other things. We recognize all those things are really important, but we have a specific need and focus for the workshop. And as you'll see, just trying to develop the JPE is going to be a heavy lift. But I don't mean to give you the impression that the JPE effort here is going to be in a vacuum. The work we're going to do here to support the development of a JPE is going to be integrated into the region-wide salmon science enterprise. The data from the effort here is also going to support spring run life cycle modeling. You're going to hear more about that in presentations today, and other scientific efforts that are used to support recovery planning for salmon. Also, the program that we're going to be working towards is going to provide the monitoring data that's going to be necessary for spring run adaptive management. So examples include habitat restoration and resources planning, such as voluntary settlement agreements, conveyance, and Central Valley Improvement Act. So as you heard from Julie, the workshop is going to be organized around several basic themes: the knowledge of life history and distribution, the monitoring enterprise, spring run identification, and some of the approaches that are available to develop population estimates. What happens after the workshop? Well, I'll be covering this in more detail on the last day, but as a quick overview, as Julie mentioned, there will be video and summaries available from the workshop so that folks can have something to refer to. But one of the first products will be a JPE peer-reviewed manuscript highlighting some of the lessons learned from the workshop. And that's targeting sometime mid next year. But more urgently, DWR has the obligation to come up with a science plan for the development of a JPE to California Department of Fish and Wildlife by this December. And so there will be a sub-team of us working on taking some of the lessons from this workshop and folding it into a science plan that will be submitted to Department of Fish and Wildlife. And then by January, the idea is that we actually start implementing some of the R&D that we're going to need as outlined in that science plan. And ultimately, the idea is to have an approved JPE approach by 2025. So throughout this timeline, our goal is to try and stay engaged with all of you for guidance. Again, this is going to be a heavy lift. We're going to require help from a lot of you. And needless to say, this is not going to be the last time we're going to be asking for input and help. Overall, we're really excited about this effort. This is a great idea for the science community to raise our game and solve an important management question. And it should substantially boost the science effort for salmon management. So with that, thank you all again for coming. And I'm really looking forward to seeing all the presentations and hearing the discussion.
Thank you, Ted. This is Julie Lineback again, your facilitator. We are going to head into a little digital polling activity now, just to get a sense of who's in the room and what are we all interested in. So I encourage you, Brandon's going to put up a slide with some instructions on menti.com. Now you can find your web browser on your smartphone or on your computer, and just type in menti.com, and then you will enter the code that is on this slide. I'm going to say it for those who are maybe just called in. The code is 8687434. And what we're all going to enter in responses to a fairly simple question to start off, which is, what is your general affiliation? And then there's just a couple more questions of characterizing your interest in this workshop and what best describes your expertise and background. We'll move into those. But this first one is just to get people warmed up and to see who's in this virtual room. So it looks like we have some responses already. I'm going to just say the instructions again for those of you who are still just getting your web browser up. Log on to menti.com. So you just put menti.com in your web browser at the top, and then it'll ask you for a code. You don't need dashes or spaces. It's all run together. So it's 8687434. Okay, and then you can see either on the shared webinar or on your own page the responses that we're getting here from folks who are in our virtual meeting here. It looks like the highest participation is from state agencies and then federal agencies. And then it looks like we have 11, 12 climbing, 14 from the private sector and academia, and then local government and a few folks from tribes, and then NGOs and other community groups. So this is nice to be able to see, since we're not in the same room together. It is really nice to be able to just get a sense of who is here, and just seeing the numbers still jumping up a little bit. Some people are still just logging on, but the ratios seem to be stabilizing and staying the same. So thanks everybody for logging on and letting us know who you're affiliated with. Let's go to the next question, which is, what best characterizes your interest in this workshop? And it looks like we already have many participating. It looks like most say, I'm interested in the implications of spring run science to management and policy. And then just below that is, I'm interested in the broader Chinook salmon science questions and implications. Only one who's just saying, I'm just here for the cool talks and discussions. I'm glad. I think we all are. and then a few, 12, who are just living and breathing Chinook salmon science. So this is good. This is good to get a sense of what everybody's looking for in this workshop. Let's go to this next question about a description of your expertise and background. Okay, so this question is open now. And for those of you who are still logging on, we are going to have some more digital polling later in the day. So even if you're just logging on now, it's just good to get it up and have some practice so you can answer the questions later. This one about expertise and background, it looks like most people are saying yes, fish expertise and background. Water management is also high. And then other, which would be very interesting, of course, to find out what that is. But under this digital poll, it's a bit of a mystery. Then, of course, some modeling, synthesis, and monitoring and genetics responses. And looks like people are still answering, but those ratios are staying the same. Thanks, everybody, for just letting us know who is in the room and your interests and your expertise. Later in the day, we will ask questions about what's the most important thing that you learned, and then what are the key questions or issues you're looking to unpack during tomorrow's session. We'll do that after these next presentations. So thanks, everybody. Let's move into the next presentation. I'm going to introduce Rachel Johnson, research fisheries biologist from NOAA Fisheries and UC Davis. And she'll be speaking about spring run distribution and life history, including updates on NOAA's 5-year viability assessment. And for this, as a background document, if you'd like to have it, it's the life history fact sheet that is in your participant packet. I'm going to hand it over to Rachel.
Hey, good morning, everybody. This morning, I'm going to be sharing with you the recent results that we have for the status of spring run Chinook salmon over this 5-year review period. We conduct these viability analyses every 5 years in support of the regional office doing the 5-year status review. And if you're hoping that I'm going to be sharing with you great news to break up this 2020 year that is just a series of pandemics, wildfires, and social unrest, I'm not going to be able to make good on that. Spring run Chinook salmon aren't doing particularly well. I do want to share some really optimistic news, and that comes from research that we're conducting, and Flora is leading this effort on our team. And what she's been able to show is that spring run in the Central Valley in the current populations have this remnant life history diversity that allows them to have this adaptive capacity to cope with droughts, which we don't see in some of the other salmon runs. So there is some hope for spring run. Next slide. So winter run Chinook salmon really take the limelight locally because of their endangered status and a lot of the focus we have on them. And nationally, NOAA Fisheries has put winter run Chinook salmon as a species in the spotlight, one of only 9 species nationally. And so they get a lot of attention both locally and nationally. Next. And we also give a lot of attention to fall run because they're delicious and they support the harvest fishery. And when they're not doing particularly well, we rally around them and we put a lot of attention around our fall run. Next. And this leaves our less delicious and less imperiled run of spring run Chinook salmon a little bit in the shadow with respect to the attention we give them in our science and some of the management emphasis. Next. And so I'm really looking forward to this workshop, which will give us an opportunity to really focus our energies around spring run. And I'm looking forward to these ongoing 3 days where we can really focus our energies on what we need to do to understand what's going on with spring run and to move the needle on their recovery. Next. So without question, I would say that Central Valley spring run, more so than any of the other Central Valley salmon, have had the greatest decline over time. Spring run Chinook salmon, some of you may or may not know, used to be co-dominant with fall run. They used to support the largest fishery. And what I'm showing you here on the left is the high elevation habitat that is the historical habitat for spring run. And with the implementation of the rim dams, what I'm showing you here in black is the high elevation habitat that's no longer accessible to spring run. Next. And what this has done is it's really selected for fall run that rely on the habitat on the valley floor. And what you can see here in this salmon color are the former habitats for spring run and the populations that have become extirpated. You can see in the San Joaquin, the entire basin has been extirpated from spring run populations. And we've selected for the valley floor, right? We selected for fall run that come in, they use the freshwater landscape for the shortest amount of time of any of the salmon. They come in already mature, they spawn, they have their babies that get out of Dodge really quickly before the summer heat of the valley floor. And it was kind of this higher elevation habitat that the spring run really thrived in. Next. And so what we see here is kind of the modern distribution, our current map of the extant populations for spring run Chinook salmon, with our salmon strongholds and our independent populations being Battle Creek, Mill, Deer, and Butte. Next. So in order to understand how spring run are doing today, we really need to take a step back and we need to see the historical context for spring run, because without doing that, we run the risk of this shifting baseline and really looking at kind of blips on a trend that doesn't really capture the full knowledge base that we have. So without question, spring run Chinook salmon have declined over time. And the shaded area that I have there is really the more recent years that we use in our viability analysis to try to understand kind of recent trends. Next. So this is what the return numbers for spring run Chinook salmon from 2001 until 2019 look like. And you can see that they indeed have declined, but they have only declined marginally compared to that longer term trajectory. And so what we're really looking at is kind of blips up in good years from kind of this baseline that's really very low. Okay, next. So how do we manage for kind of these resilient populations for spring run, and what would we lose if they went extinct? So spring run Chinook salmon are unique. They're unique genetically, they're unique behaviorally because of their underlying genetics, and they have had hundreds and thousands of years to have traits that allow them to co-evolve with their special habitat template that makes them unique. They're genetically unique from the other West Coast runs of Chinook salmon that are in these other evolutionary significant units here in the colored portion of the map. And within the Central Valley, we have a significant variation in run timing of Chinook salmon. And because they are reproductively isolated in space and time, this allows them to have these locally adapted capacities for really fine-tuned matching between their genetics and the habitat template that makes them successful. So if we look at spring run here in the bottom, spring run historically used the spring hydrograph to ascend into these high elevation habitats that were cold. And these cold habitats allowed them to delay maturation. They hung out in the summertime in this cold water and matured, and then they spawned in the fall. And the juveniles even took advantage of this cold water in the sense that they can live up to, well, they would use the cold water habitat and for up to a year, which would allow them to over summer and to get really large. They were huge. They used to be huge as yearlings when they would outmigrate into the ocean as yearling sizes. Next. And so what allows us to have this kind of remarkable diversity in Central Valley and in kind of these behavioral diversity that we see in spring run? Well, you can think about those metrics as a viability pyramid, where we often think of abundance of spring run. We want more of them, right? We want more spring run fish, and that's at the pinnacle, at the top of this pyramid. And abundance is a really important metric because it's an integrator of all of these other factors that influence the abundance of, for example, spring run. But we would be remiss in just focusing on abundance and thinking we just want more spring run without doing the hard work and recognizing that in order to have abundant spring run, it's on a foundation of factors that influence that. And at the base of that foundation is habitat capacity, the amount of good quality habitat, the variability of that habitat that can support kind of the diversity that we see. And so a lot of our focus is on kind of the habitat complexity and the biocomplexity and that environmental variability to support spring run Chinook salmon. Next. And spring run Chinook salmon, like all of our Central Valley salmon, have evolved and have co-evolved with this innate ability to cope with wildly variable climate. This is one of my favorite plots. It's not precipitation across the US, but it's also not a fire map, and it's also not an air quality map. It is the variation in precipitation across the landscape. And what you can see here is in the California Central Valley that it's really dynamic, that these animals evolve to cope with this really variable environment that has always been the case in California with these salmon. Next. And so salmon have evolved to cope with this variable climate. They did not go extinct during the mega droughts. Spring run did not go extinct during the historical time period during the Dust Bowl. And this is a picture of Oroville during our modern drought. Next. They also were able to evolve and cope with these environmental extremes, such as these big floods. Similarly, this is a picture of Oroville. Above it is during the drought time period, and below it is during the most recent highest water year we've had in 2017. And you should know these two pictures of modern climate variation are just 2 years apart, right? And they're also the component in our 5-year status review that I will be emphasizing and highlighting for you today. Next. So again, the 2017 water year is the juvenile period that results in these 2019 returns, and it was the wettest year on record. And then we also have in the viability analysis these drought years as well. So how do we assess how well spring run did during that period of time? Next. So we use a framework that was developed by Steve Lindley and a number of stakeholders and diverse scientists that came together during the technical review team period when the fish were first listed. And what you can see here is the framework that's put forward to try to assess the extent to which the populations are at high, moderate, or low risk of extinction. And these are all based on the escapement data, so the adult counts that CDF&W leads. So for spring run, we look at the total population size, which is the sum of the 3 most recent years of returns. We also look at the population decline, which is the run sizes over the last 10 years and the slope of that, whether or not it's positive, we're seeing positive population growth, or whether or not we have steep declines, and the magnitude of those declines. We also evaluate the catastrophic, if there's been any kind of catastrophic declines, and that is the largest decline that is observed over 10 generations. So it's the drop in one generation of time, but over 10 years, and what the maximum decline is over that period of time. And then also the extent to which we have hatchery influence to our populations. Okay, next. So how are spring run doing using these criteria? Well, this is the return data from CDF&W, and you can see the most recent 5 years are in these gray bands. And you can see that they're in decline, and the most recent 5 years are worse than the previous 5 years. And I should also note that we have early data from Doug Killam and Matt Johnson for 2020. So the adult spring run that are holding this summer that haven't yet spawned. And you can see for Mill Creek, the estimate is 73, and for Deer Creek, it's 90 individuals, which just makes me hold my breath. That is not a lot of individuals. Next. And when we look at our portfolio of our salmon strongholds for spring run, we do see that Butte Creek is really holding its own. Relatively speaking, it in 2019 is showing a return to an increased number. If you recall, that is the wettest year on record, and the leading hypothesis around what helps Butte Creek do so well annually is that they're one of the only spring run populations that are still connected to their floodplain. You can see that the other populations, even though they are less dire than perhaps Mill and Deer Creek, you can see that within the last 5-year period, they have reached their decadal low. So they've had a year where their return numbers are the lowest within the last 10 years. Okay, next. So what is the cause of this? Well, these adult returns are the cohorts that experienced this huge drought series between 2012 and 2015. Some of you may not even recall. I mean, a lot has changed in these 5 years, but it's, to some of us, there's not we have a lot of recent history around kind of the impacts of those droughts, and we're seeing the impacts of those droughts in those adult returns. Okay, next. Those fish were also confronted with terrible warm ocean conditions. If you guys remember, not only were they confronted with the drought, but it was also really warm sea surface temperatures and the warm blob. So those fish, that cohort, they were hot their entire life cycle. Okay, next. So what's the cumulative, the effect, the cumulative effect on these? And so again, these are the extinction risk criteria that I shared with you earlier. The population size, the run size, the declining trend, and the percent drop in one generation. Getting a little bit of feedback. I don't know if anybody else is able to hear okay. What I've highlighted here in red are the metrics that put them at a high risk of extinction. And if there's one metric that's high, then the population is considered at a high risk of extinction. So you can see for 2020 that all the populations are considered at a high risk of extinction, with the exception of Butte Creek that continues to hold their own. Okay, next. So that's the summary of the status of spring run today, and they've been heavy hit in the last 5 years. What I'm going to do now is I'm going to shift gears, and I'm going to try to bring some hope to the science of spring run and their resiliency by talking a little bit about their life history diversity and work that Flora Corleone is leading on our team. I'm also going to be showing some success stories around reintroduction and recolonization. Okay, next. So spring run Chinook salmon have a very wide range of behaviors that they have in their juvenile life stage, where they have a lot of diversity in the amount of time they spend on the freshwater landscape. They do have that yearling, the characteristic yearling life history strategy that has them over summering and leaving the next calendar year. And this diversity is really important. It's not that different from the way that we think about the diversity that we see in the juveniles has spreads juveniles across the landscape, and it spreads risk in space and time. And so I'm getting an error message that you guys might not be able to see the screen. I'm going to keep pushing forward.
Yeah. Rachel, just keep talking, and I think that Brandon will address it.
Sounds good. So the diversity that we see in spring run is no different than we think of our own financial investments, where if you had one stock and it was really volatile, there might be a lot of booms and busts. But if you have invested your funds across mutual funds or a diversity of portfolios, that helps to buffer these boom and busts. And in theory, it's supposed to allow one to have an overall increase in investment over time. And salmon do the very same thing. Next, if we can advance. We might be stuck on this slide forever. Perfect. So the work that we've been developing takes advantage of the fact that we have natural markers in our underlying geology that allow us to track the juveniles in their habitat use over time and reconstruct what that is. Next. And so the way that we use that, we showed you that variation across the landscape, but we've invested a lot of our energy, and we have a lot of variation in strontium isotopes and in our geology in the Central Valley, just right here in California in our salmon watersheds. And what this allows us to do is to use the underlying rocks and the diversity in that, and it's the incorporation of strontium 8786 into their ear bones on a daily basis that allows us to track and to use like a fingerprint how long fish spend in that habitat before they outmigrate, the size at which they leave it, and it allows us to reconstruct that movement pattern when we look at the adult returns, and I'll show you how that works a little bit. Okay, next. And so up in the upper left-hand corner, you'll see it's a sectioned otolith, and you can see from the very core is when it's a very small juvenile, and each of those spots is a laser that's been taken that material and measured in a mass spectrometer, and it measures that signature, that fingerprint that I was sharing with you. And so, Brandon, we're going to want to kind of go through these a little bit quickly as the animation moves. And so, what you can see is that as the juvenile grows in Mill Creek, that they use mom's yolk, and they reach the Mill Creek fingerprint signature I mentioned next. And that individual grows large, and then it rears for a longer amount of time in the Sacramento River, and then it moves to the ocean. So you can click next. Again, it's rearing in the Sacramento River. And lastly, it grows large, and then it goes to the ocean. And so we're able to reconstruct its movement patterns by looking at the surrounding isotopic ratios. Okay, next. And so what we saw before was an early outmigrant that spent a very little bit amount of time. And now what I'm showing you is a profile of a yearling. Next. So once that juvenile feeds on its maternal yolk, you can see that it rears for a long time in the Mill Creek. Next, until it migrates to the ocean. I'm just going to pause right here because I'm seeing a lot of threads around the inability to see the presentation. And I just want to check in with the organizers to see if there's anything that needs to happen here.
Thanks, Rachel. I'm seeing the same. And I'm getting some feedback. I think Brandon might be trying to address. Brandon, do you want to, I just invite you to say anything to everybody about maybe troubleshooting the webinar view?
Yeah, this is Brandon. I'm not seeing any issues on my end in terms of sharing it, but maybe I need to change to sharing my screen instead.
Oh, it's patchy. That's awesome. This is crazy. I wonder what contributes to IT patchiness.
Are you able to see slides, or is it still?
I'm happy to keep on keeping on, or staying or pausing, whatever you guys recommend.
I think at this point, I would just suggest for those folks who are having difficulties to log out, log back in, see if that works, check your internet connection. And I see some people have tried that, and Brandon, if you have any other suggestions, of course, but I think we do need to keep going.
Okay, sounds good.
This is Lita. I've seen another suggestion that folks have joined through the browser instead of the Teams app. So if you've tried all of the other things and it's still not working, please also try to join through the browser.
Okay. Thank you, Lita.
Sounds good. All right.
Okay, Rachel.
I know, Brandon, you're wildly busy over there, but next slide. All right. So what did we see when we actually looked at Mill and Deer Creek adult survivors using this otolith tool? What we can see is in the adult survivors, we can reconstruct what they did when they were little. And we can see that a lot of the surviving adults left as early, intermediate, and late individuals. So we're seeing survivors that use a diversity of juveniles to be successful. Next.
I just want to remind everybody to go ahead and mute yourself if you're not on mute, so we can reduce background noise.
And what I can share about this late distribution is that those are the yearling ones. And what you can see here is now I'm plotting work that Flora has been doing that shows that when we look at the size that these fish leave fresh water, that the fish that left is really small fry, and those that left intermediately, which means that they stayed in Mill Creek longer, that they left fresh water around the same time. So that means that those early dispersers reared somewhere else until they got to a large enough size to enter the ocean. And then this next plot is, I think, one of the most exciting findings we've had so far. Next, please. What you can see here is when you break them out by water year types in terms of the successful outmigration strategies, what you can see here on the otolith radius, the larger size, is that we see in some years, in 2012 and 2018, the yearlings are the ones who survived and contributed to the adult returns in those years. Next. So what this suggests is that in these years that happened to be critically dry and dry years, that those juveniles that stayed in Mill and Deer Creek and didn't leave to the valley floor in the hot drought ended up being the survivors. And so this life history strategy is one of the coping strategies we see in spring run Chinook salmon that allowed them to persist over the most recent drought. Next. And when we compare Mill and Deer Creek with Butte Creek, we see a different pattern. So we see with Butte Creek, when you look at their rotary screw trap data, we do see early in the season, especially kind of this bimodal distribution between really large yearling fish and kind of early out migrants. And when you plot their adult survival, what you see here, I've overlaid in kind of that salmon color, you can see Butte Creek on the top, that there's not three distributions like what we saw with Mill Creek survivors. We actually see that they have a singular out-migration strategy that seems to work for them. Next. Next. And so when you compare spring run on the left, and these are the data I already showed you, to fall run, the fall run on the Stanislaus River, where we also have a significant time series, you see that there's a lot more among year variation in spring run than what we saw in fall run, which was just a very weakened portfolio where only kind of one of those out-migration strategies, no matter if it was a wet, dry, any kind of year, kind of that middle sized fish seems to be the prevailing successful strategy. Next. And so what does this mean for our salmon? So when we look at the likelihood of Central Valley salmon thriving in the climate future, the most recent climate vulnerability assessment that Lisa Crozier led with myself and a number of scientists from the Northwest Fisheries Science Center and the Southwest Fisheries Science Center and our academic partners, it shows that Central Valley salmon are the highest risk populations for extinction in the climate future due to temperature warming. So what do we need to do to have kind of resilient, temperature resilient populations moving forward? Next. Well, one of the things that our recovery plan points to is spreading the risk with spatial structure and diversity. So being able to allow, instead of all the spring run populations that are all clustered up in that upper region that are totally vulnerable to a big volcanic event or wildfires or the same kind of environmental disaster, if we spread them out and have redundancy in their populations like they historically had, and if they had access to that cold water, then that would be one way that we could build in that resiliency back into spring run populations. Next. And another thing we need to be mindful of is, and because this is a life history diversity talk, is that sometimes populations that look seemingly unimpressive can be incredibly important for resilient populations. And so what I'm showing you here are dependent populations, so kind of smaller populations of spring run. Put your eyes on Big Chico Creek. In some years, the number of spring run returning to Big Chico Creek are higher than in some years in our independent kind of salmon stronghold populations. And there's two reasons to find this to be kind of important to be focusing on. The first one is that these smaller tributaries, sometimes they're pretty inhospitable. So in Big Chico Creek, if you get a bunch of adults returning there, but due to temperatures or passage barriers or lack of improvement in restoration, then those populations become they become sinks for this threatened fish, right? But on the flip side, if those conditions are favorable, some of these populations might be the most important ones when we think about where our resiliency is going to be coming from for spring run in the climate future. Next. We also see a lot of hope and diversity around spring running fish showing up on San Joaquin tributaries. These are data from the Stanislaus River. So you can see in some years, the numbers of spring running fish returning to the Stanislaus outpace some of our other populations. And so we shouldn't ignore where we think our focus should be just because these might be the most important ones in our climate future. I also want to tip my hat to the San Joaquin Restoration Program that had one of the greatest success stories of a comeback. And everybody loves an underdog, and this is that story. In 2019, they had their first salmon come back from their reintroduction program, and that river had been dry for 65 years. And so, so we see success on the landscape, and we need to kind of marshal and celebrate those successes. And lastly, next. In conclusion, we see that spring run today are worse than they were just 5 years ago in their most previous status review. It's likely a combination of poor freshwater and ocean conditions. And we highlight that in Mill Creek and Deer Creek, that the survivors there, that the yearlings in particular, seem to be an important component of their resilience piece during drought. We see spring running salmon reappearing on San Joaquin tributaries, suggesting that we should keep our eyes on kind of natural recolonization processes. It's these locally adapted self-sustaining populations that are the goal for recovery. And then lastly, it's hard to imagine that we are going to be able to recover spring run populations on a fall run template. And so we really need to be thinking about reconnecting spring run to their historical landscapes that they have co-evolved to thrive under, especially in the climate future. And lastly, this is just a summary slide and graphic that how do we build resiliency next? The first thing we need to do is shine a light on spring run, which we have done and are continuing to do with this workshop. So I think this is absolutely the first step. How do we change the declining arrow to being rebuilding? Well, we talked about a few of the things. We know that in 2020, that spring run are worse off than they were in the last 5 years. And so what do we need to do to make 2025 kind of move the needle in the other direction? Next. I'd like to offer that perhaps life history diversity is something that we need to find ways to support in order to rebuild these populations. And lastly, again, next, that without kind of restoring these habitat templates, are being critical to being able to support these resilient salmon populations. And that's the last slide. I'd like to just acknowledge the heavy lift that CDFNW, U.S. Fish and Wildlife Service, and others do for monitoring spring run and are the shining lights of all of the work for what we know for spring run. And with that, I will pass the baton back over to Julie and look forward to Flora's presentation and the others for the day. So thank you. And I guess there'll be time later for questions. Thanks.
That's right, Rachel. Thanks so much. Brandon, will you help me with my feedback? There you go. It's funny how with these webinars, you start out with good audio and sometimes it changes. I want to, with that in mind, I want to address the technical issues. Some people were having trouble seeing the webinar. I do see notes that some people are having success viewing it in the browser. Unfortunately, we cannot send out these presentations due to their inclusion of unpublished work at this time. So I apologize for that, but please experiment with the browser if you are having difficulties seeing. Also, you can email engage@deltacouncil.ca.gov, and there is actually a whole webinar team. Brandon is at the point of it, so you can access other people with that. I want to now introduce Flora Cordoliani, project scientist and UCSD affiliated with NOAA Fisheries, and she will be addressing spring run state of monitoring and key gaps. Go ahead, Flora.
Can you hear me? Thank you, Julie.
Yes, we can hear you.
Okay, perfect. So I'm Flora Cordoliani, and I'm a project scientist with UCSD and NOAA Fisheries, and I'm going to talk to you about monitoring of the Sacramento River drainage spring run Chinook and the data gaps and challenges that we've been identifying in the fact sheet. So next. And I'm sorry, Brandon, but I realize I have way too many animations. So I'm going to ask you a lot of next. Okay. So I just wanted to take a few minutes to talk about this map that I made for most of the fact sheets, and because there was some discussion on the classification. And so you can see on this map that I have three types of population, three classes or groups for spring run population. And this classification is based on what was proposed by Lindley et al. In 2004 in their study of the structure of Central Valley spring run Chinook population. And this was based on few criteria such as increased isolation, minimum basin size, and substantial genetic differentiation. And so based on this classification, we have 4 independent populations. So you can click on next and then next again as well. So the 4 independent populations are Battle Creek, Mill, Deer, and Butte Creeks. And that means that they were historically not sustainably altered by exchanges of individuals with other populations. The second group that we have in purple are independent populations such as Clear Creek, Cottonwood, Bigham Creek, Antelope Creek, Big Chico Creek. And those populations mean that they likely would have not persisted without immigration from other streams. In addition to that, Spring Run mainstem, Sacramento River mainstem population was considered as dependent as well because they likely did not spawn in the mainstem Sacramento River before the construction of Keswick and Shasta Dam. And it is believed that serious hybridization has occurred with foreign fish, so that's why they were categorized as dependent. And then finally, in pink, you can see at the bottom, Feather and Yuba River population. They were historically independent population, and I consider them here as hatchery influenced population due to the genetic proximity with the Feather River hatchery adults and the nidal spawners, and the large presence of hatchery fish from the Feather River hatchery among the in-river spawners. So those are the populations that I've been focusing on for this study, for their monitoring, and you can click on next. And next again, probably. And so the long-term monitoring of spring run Chinook salmon is performed by a variety of agencies, state and federal, as well as some universities in the Central Valley. And so the goal of this workshop was to evaluate whether this monitoring can be used to adequately assess the influence of water operations and to see if how those operations will impact their dynamics and overall persistence. So I'm going to focus on 2 types of monitoring that is being done in the Central Valley, which is adult monitoring of the spawners and the freshwater juvenile monitoring. Next. So I'm going to start with the adult monitoring. So next. Thank you. And so different types of methods are used for adult monitoring, so such as red survey, that went too fast, red survey, snorkel survey, carcass survey, and video monitoring. And agencies usually use a combination of one or multiple methods for each spring run watershed. You can do next now, Brendan. And this adult monitoring are different objectives, and you can click next like 3 times, I think. One is to quantify the total escapement number, so the number of adults returning to the spawning ground, to monitor summer holding and spawning, which includes the timing, the success, and spatial distribution. It could also, one of the objectives could be to quantify the number of eggs and fry generated per spawner. Next. But as we're going to see in the next slide, various watershed-specific challenges and uncertainties in collecting adult data might impact the accuracy of a spring run juvenile production estimate development. So I, with some very elaborate schematics, I tried to summarize those challenges. And the first one that we identified for adult monitoring was inconsistent assessment of sampling efficiency. And so as you can see on this little diagram, the error in the number of adult spawners observed related to sampling uncertainty is sometimes not evaluated. And that could potentially create a bias in the escapement numbers reported. And you can next. In multiple watersheds, video monitoring has been implemented. And so one of the solutions would be to estimate the video count error. This error could be a combination of processing error, of observer error, or equipment downtime error. And in Battle Creek, for instance, the passage estimate equation is used to expand adult counts during video monitoring outage and poor video quality. So one of the solutions would be to use this estimate during video monitoring. Next, the second solution that could be implemented is to use some mark recapture carcass survey. So next, Brendan, I think it's just one either text. And so carcass survey, back.
Sorry,
I bet those slides are really heavy and they are hard to do. Is that the problem, Brendan?
Flora, is this the right slide with the?
Can you go back one slide? I guess it takes some time to actually just go through the animation. Here we go. Okay, so another possibility that we can see in some of the watersheds, such as Butte Creek, is the implementation of a mark recapture carcass survey. And the idea is that this technique employs physical count of all carcasses during the period of interest and develops an extinction factor for carcasses that are not encountered during the physical count. And several models are used to estimate this extinction factor and estimate the final adult number found in the stream. And I just mentioned two models here. The Peterson model is the simplest model and is useful in developing an estimate when you have major disruption to the sampling schedule, which happens in some of the watershed where carcass recovery is difficult. And it treats the entire survey as just two periods, one tagging period and one recapture period. So it's not the most accurate, but it's the easiest to implement. And the second one is the Cormack-Jody-Sieber model, which is the one that is used, for instance, in Butte Creek. And it's also the one recommended in the Central Valley Chinook Salmon in River Escapement Monitoring Plan that was developed by Fish and Wildlife and by the Pacific Marine Fishery Council in 2010. And it provides a more accurate estimate of adult abundance, estimating an extinction factor, but it requires a more intensive mark recapture survey methodology. Next. Next, Brendan.
Flora, I just want to make sure because there is a little bit of a delay. Is it the slide that says lack of adult holding and pre-spawning?
Yes.
Okay.
So the second challenge that was identified is, as Rachel mentioned, spring run has a unique life history and life cycle where they will return to the spawning ground in the summer and hold in cold water pools before spawning in the fall. And so making sure that adult holding and pre-spawning mortality is assessed might be an important part of the adult monitoring, and it's not always performed properly. And so or accounted for when developing estimates of escapement. So next. So for instance, if abundance estimates commonly from adult sampling performed during the upstream migration in the early spring, or early summer, this could create a discrepancy between escapement and the actual spawner number, with the potential of overestimation of the spawner abundance. So some solution could be to combine the video monitoring that is performed usually at the entrance of the watershed with a spawning survey that's performed during the spawning time period in the fall, such as red survey, which is what is currently done in Mill Creek, for instance, and that will allow us to estimate the difference between pre-spawning and spawning numbers. Next, another solution is to develop again a pre-spawning mark recapture carcass survey. And in Butte Creek, this is what is implemented. So in Butte Creek, for instance, large pre-spawning mortality events have been observed in the past. So this mission of pre-spawning mortality is performed by using a variety of sampling methods. So you have snorkel survey conducted in early summer in conjunction with video monitoring that provides an escapement estimate before any pre-spawning mortality. And then a pre-spawning carcass survey followed by a spawning carcass survey in the fall are conducted to evaluate pre-spawning mortality and to provide an alternative spawner estimate to compare to the snorkel escapement. So that would be one of the solutions, for instance, to be able to account for this mortality. Next. The next challenge that we identified is spatiotemporal overlap of spawning of spring and fall run spawners. And this is happening in a lot of different watersheds in the Central Valley, such as Feather River, the Mason Sacramento River, in the Yuba River. And so being able to extract and report accurate estimate of spring run escapement is challenging sometimes. And this is further complicated by the lack of a suitable means of distinguishing spring from fall-run adults during the spawning period. And so one of the possible solutions next that has been implemented in Clear Creek, for instance, is to use a temporary spatiotemporal barrier, such as a segregation weir, that allows to separate in time and space spring from fall-run adults. And you can click next again. And another option as well is to be able to collect enough tissue samples and perform genetic identification of those spawners. But for that, it requires recovering enough carcasses to do tissue sampling, to perform the tissue sampling. And this also probably requires to secure reliable funding to collect those tissue and run genetic analysis. So that comes as well with some potential challenges. Next. And finally, the last challenge that has been identified in adult monitoring is sometimes insufficient information on adult length and sex data. So extracting and reporting accurate number of spring run escapements is sometimes challenging because of, the reporting of the number of eggs produced is sometimes challenging because of the lack of information on the length of the fish and of the sex, which kind of determine the amount of eggs that are going to be produced by those spawners. And next. So again, to collect information on those fish size and on the sex, one solution is to perform carcass survey, which again might be difficult in some watersheds because of the difficulty to recover those carcasses. And another solution next would be to use actually some surrogate data, so using population information from other spring run population or watersheds, such as, for instance, the Feather River hatchery spring run, to be able to come up with some productivity values for each spring run population. And next. So based on some comments from different agencies that we had, that I had when I developed the fact sheet, I kind of wanted to have a table that summarized those water-specific challenges and what are the main challenges for each watershed and what are the potential solutions. And as you can see on this table, I'm not going to be able to go through all those watersheds because of the sake of time, but each watershed has one or several challenges that I identified, and I'm sure there are maybe other challenges that are also important that I missed. But I think it's a first start to just think about discussion for tomorrow breakout session and think about what do we need to focus on in terms of monitoring for spring run adults. And just, you can go next. This is the first part of the table, and we have a second part here. And so in an attempt to identify all this, I just want to mention that for spring and fall run overlap, as I mentioned, which is pretty common in several watersheds, so such as the river and Yuba River, genetic identification could be one of the solutions, but I realize that this is something that we will hear more about in other presentation and that might be challenging as well. But hopefully we will be able to figure out some solutions. Okay, so next. So now let's go to juvenile monitoring for spring run population. So again, several methods are used in the Central Valley to monitor spring run Chinook. The most common is using a rotary screw trap at the base of the watershed, and that's what you see in the map with the little yellow star icon. And also you can find a series of sampling such as trawling and beach staining in the migratory corridor. So for instance, the Sacramento River and the Delta. And for the study of the movement of those juveniles and the survival throughout their migratory corridor from the Nile stream to the ocean, several acoustic tagging studies and coded wire tag studies have been implemented with spring run Chinook fry or smolt. And also, in addition to that, as you've seen with Rachel's presentation, the use of otoliths has been used to look at life history diversity and the size and timing of migration for those juveniles. And so again, for each watershed, a combination of one or multiple methods are usually implemented. So next. And you can click next 3 or 4 times, I think. So the objectives, again, are multiple and include to assess the relative abundance of juvenile salmon, to quantify the salmon production, so the total number of juvenile migrating past the location, and to collect juvenile life history information, such as migration timing and size distribution, as I mentioned. But again, as for adult monitoring, various watershed-specific challenges and uncertainties exist in juvenile data collection that could have an impact on the accuracy of the spring run juvenile production estimates. So let's look at those challenges next. So the first challenge identified is the lack of sampling efficiency. So to expand raw juvenile capture numbers to total abundance values, trap efficiency studies need to be performed during the trapping season. And only a few spring watersheds currently conduct trap efficiency trials at the levels necessary to reliably expand estimates. And one of them that is doing this is Battle Creek, for instance. But in some watersheds, such as Butte Creek, Mill Creek, and Deer Creek, for instance, due to the high frequency of high flow events and other personal issues, access to larger fish and the access to large fish numbers that is difficult that sometimes prevented the development of trap efficiency. So one solution, next, is to develop a trap efficiency methodology that uses surrogate fish in those tributaries, such as hatchery, forerun, or spring run juveniles, that could be used for those trials if possible. And next, another solution would be to use efficiency estimates from other tributaries, so using trap efficiency surrogates, but that also goes with a series of assumptions. So, of course, such as the idea that we have a similar flow dynamics that is observed in the two watersheds. So again, not something that is easy to figure out, but hopefully this workshop will help find solutions. Next. So another challenge that we identified is the need for better run identification. So again, like for adults, it is possible to have an overlap of spring run and other runs, such as fall run Chinook salmon juvenile, in time and space in the spring run watershed, as well as in the Sacramento River and Delta. And so next, to better identify those fish, one solution again is to collect enough tissue sample and run genetic analysis on them to make sure that the fish that are caught are actually spring run. Next. Another solution that is developed currently at Nice Landing Valley Screw Trap is actually to develop a length height probabilistic model. So instead of just using the length height criteria that is currently used and we know has some flaws for spring run, being able to use the probabilistic model will allow to take into account identification uncertainty, which might improve the identification accuracy of spring run. Next. Another challenge that was identified is insufficient information on juvenile survival estimates. So the estimation of fry to smolt and smolt survival from the Nile stream to the Delta might be required to develop a juvenile production estimate. However, spring run fry survival are difficult to estimate because of the difficulty to track those fry because of their small size and the absence of large codified tag programs for spring run population that could be used to estimate fry survival. One of the exception is the Feather River hatchery spring run population, where spring run Chinook fry are 100% coded wire tag before being released in the river. So if a large number of tagged fry from the hatchery are recovered in the delta, this information could be used to estimate in-stream fry survival. Another solution, you can click next actually. Another solution is to develop some pit tagging study. Pit tags allow to mark and track par-sized juveniles, so of about 50 millimeter. And development of this study in spring run stream could allow to assess fry to smolt survival. Next. Another solution that could be implemented is actually to use surrogate survival estimates. So again, because we know spring run and fall run fry are found in the system at similar time and size, we could use fry survival from fall run studies instead of spring run population. Next. And then if we look at smolt survival from the nether stream to the delta, I think you can click next. With new advances in acoustic tagging technology, biotelemetry studies have been very well-established tool in estimating smolt survival in the Central Valley, and it has been used for some population of spring run Chinook, such as mule deer and Peace Creek. However, most of those tagging studies occurred in the last drought, so they are likely not representing a suite of hydrological conditions that spring run smolt are experiencing. And additionally, because of the small number of smolt that were tagged, especially in Mule and Deer Creek, the survival to the delta is associated with large error margin. So securing reliable funding and having the implementation of a long-term acoustic tagging network and study could help provide better estimation of survival of the spring run smolt to the delta. Next. And again, another solution could be to use surrogate survival estimate of fall run fish, of fall run smolt, for instance, tagged in Sacramento River, which has been done as well in the past. And late fall run could be used, late fall run survival in the Sacramento River could be used as surrogate for yearling, spring run yearling, because they outmigrate at similar sizes during the fall. So that's something as well that could be considered. Next. And so as for adult monitoring, I developed this juvenile watershed-specific monitoring table. So you can see the different watersheds, the monitoring methods used, the main challenges, and some potential solution. And so you can see that what is recurring a lot for juvenile monitoring is the absence of abundance estimates, which is linked to the fact that no trap efficiency is occurring in those different watersheds, and then the spring and the overlap of spring run Chinook salmon with fall run or other run of Chinook salmon from the Central Valley, which might require better genetic identification methods deployed. And you can click next. And just I want to mention that, so this is the next part, and so it's summarizing what's happening in Peace Creek, Sacramento River, Feather River, River, and then several parts of the Delta. And so, for instance, at Chips Island, there's currently a paired coded wire tag and acoustic tagging methodology that has been developed using winter run hatchery fish to generate accurate trawl efficiency estimate and abundance estimate of juvenile winter run Chinook at this location. And so a similar approach could be used and combined with genetic identification and would be to be able to estimate spring run Chinook salmon juvenile abundance at Chips Island. And if this approach can be developed for Chips Island, it can also be developed at other trawl stations such as Sherwood Harbor. So that could be a way of estimating juvenile abundance of spring run entering the delta. So next. And so I wanted to finish with the key questions that were suggested in the fact sheet for monitoring. So you can click next 3 times, I think, or 4 times. And so just a reminder again for the breakout session that what we really would like to know is what are the key monitoring gaps that need to be developed that we would need for the development of the JPE, which necessary information is available or currently missing to apply this JPE approach, what are the trade-offs to filling those data information gaps, and is the JPE development more critical for some population or some location more than others? Next. And with that, I would like to thank the Delta Stewardship Council for developing this workshop and all the agencies that actually are doing the in-the-ground monitoring and also helped a lot with the development of the fact sheet. And thank you all for next. Thank you for listening.
Thank you, Flora. This is Julie Lineback again, your facilitator. We will open just a few minutes of question and answer here. Now, this is just on Rachel's presentation and Flora's presentation. And I want to start with asking you to use the chat, just putting your name and affiliation that will indicate that you want to be in the queue. I will let you know we are going to just spend maybe 5 to 7 minutes on this because we're running a little behind. And I want to start out with James Hobbs, I believe with Fish and Wildlife Service. He had a comment earlier. And so, James, would you go ahead and unmute yourself so you can ask your question?
Oh, yeah, it was a kind of a simple technical question, but I was wondering why the spring run fish that Rachel was showing had a elevated isotope core, even though the natal tributary is like 704. She had a thought on that.
Yeah, can you hear me?
Yes.
Yep.
Okay. Yeah, we actually do see for spring run as well as winter run a surprising. We see kind of the maternal marine signature in our reconstructions, which challenges our conceptual models around where vitellogenesis occurs for both of those runs. I agree with you. It's surprising that is a result.
Yeah, just curious.
Yeah.
Thank you. Thanks, James and Rachel. I see now I have another question from Wasang Jin from the State Board. Would you like to unmute yourself and ask it yourself?
Sure, thank you. Just have, I guess, 2-part question, if you don't mind. One is what is the general proportion of, say, juvenile migration and the yearling migration or migrants for in general perspective, and then also for each specific tributary, is the proportion of that juvenile migrating or yearling migrating out, is that sort of a generally relatively constant for a certain given stream or river, or could that change depending on the environmental conditions? As I said, the hydrology or maybe temperature conditions or whatever other issues. Thank you.
Flora, did you want to take that, or do you want me to attempt to answer that?
The general proportion actually varies among years. It depends, as Rachel showed with the plot for the different years. It actually is very different among the different years. So some, as Rachel showed, some years it's a majority of yearling, whereas in some years it might be the yearling component might be a minority compared to the other migration strategies. And then yes.
I was just going to say, you raise a really good point, though. We really don't have a really good sense of the expression of the different life history strategies. Some people claim that, well, that the monitoring of yearlings is really hard, right? They might evade rotary screw traps much easier than sub yearlings would. So we really do need to kind of get a better estimate of kind of the outmigration diversity in kind of a quantitative way to be able to see whether or not those that we see as survivors whether or not it's an issue of survivorship or whether or not it's an issue of expression. So I think we just need to do a lot more work around kind of looking at different populations and potentially getting better estimates of what's actually being produced from the different tributaries. I can share that I've been told that the two tributaries that have higher elevation habitat, so Mill and Deer Creek, are the ones that tend to produce or have the opportunity to have cold water habitat through the summer to produce the yearling strategy. I'm not sure how rare or common that is across other systems.
Thanks, Rachel. This is going to be the last question. I see Louise Conrad from Delta Stewardship Council has a question. So we'll go with that one, and then we'll move into our break. I'm going to hand it over to Louise.
Hi, Rachel and Flora. Thank you so much for your excellent presentations. I already feel more educated. I noted that, Rachel, at the end of your presentation, you made a point that reintroduction would be important for recovery. And I also noted from Flora's presentation that we have a hatchery program at the Feather River Hatchery. You talked about a little bit about the tagging there. I'm wondering, can either of you speak to what, for recovery purposes, how the current program at Feather River Hatchery would look different to support spring run salmon? What would a recovery program that includes supplementation need to involve?
That's a really good question, and it's actually an area of active work for the West Coast Regional Office for NOAA as it relates to Yuba River reintroductions of spring run. And as you can imagine, like anything related to California fish and salmon, there are questions around genetics. So like, what stock would you use? How would that look? And there are people with better minds than mine who are actively thinking about those questions. But yeah, there is, for the reintroduction program on the San Joaquin side, Feather River, spring run were fall run first, with the ultimate goal of spring run being the target kind of seed stock for that effort. But there is a lot of complexity around making sure that you're not impacting the resources that we have in order to kind of build in those stocks.
Thank you, Rachel.
Thanks, Louise, for that question. I'm going to start our break now. It is 10:41 by my clock, and we will start with Daphne Gill and her presentation at 10:50. So you can just leave, you just mute yourself, walk away, do whatever you need to do, and we'll be back at 10:50. Thanks, everybody. Welcome back, everybody. This is Julie Lineback with Kearns and West, your facilitator for this workshop today. Welcome back to the Sacramento River Drainage Spring Run Chinook Salmon workshop on the state of the science for population estimates. I want to remind folks, if you haven't been here for the morning, that the browser seems to be working better to be able to see shared webinar documents. And that if you have a need for troubleshooting, go ahead and email engage@deltacouncil.ca.gov and they can help you out. I want to introduce now Daphne Gill, Environmental Program Manager with Department of Water Resources, who's going to talk about tools for spring run identification. And I just want to remind folks that there is a really rich background document called Run Identification Tools Fact Sheet. And Daphne, I'm handing it over to you.
Great, thank you. And I just wanted to tell everyone my video is on, but I'm calling in with my phone, so you may not be able to see me, and that's just because my internet drops so frequently. So I apologize if you're not seeing my face, but I'm there. Before I begin, I'd just like to acknowledge my co-authors that also authored the fact sheet. And also to say that tools for spring run identification is a very active and fertile area of research at the moment. And so I'm going to be giving an overview of kind of the state of the science, but there are experts, and I talk about some of their work in this presentation. So in the question and answer period that comes later, just be aware that I may bump some questions to specific experts because I know that it's their area. So looking forward to that. So next slide, please. Great. So as we've already heard about this morning, we've had quite a bit of background on Chinook salmon run type, but run refers to season of adult entry into fresh water, and we have 4 seasonal runs that co-occur in the Sacramento-San Joaquin River system, and these are spring, fall, late fall, and winter, and there are no morphological differences between runs. And the spring run are unique in that they have tribal significance and are desirable for their high fat content. And so this map here is one of many maps that you've seen this morning. It seems like we're all starting with maps that show the historical salmon producing streams of the Central Valley drainage. And then of course, black X's are where salmon are no longer found as a result of blocking due to dam access. And so next slide, please. And so as we've already heard, we have too far, go back one, please. We have 2 listed runs. So spring run are federal and state listed threatened, and then winter run are federal and state listed endangered. And so it's very important that we have an accurate means to assess run ID so that we can effectively manage these species and especially take of both. Next slide, please. And so variation in life history causes overlap in timing of each of these runs. And just as an example, spring and winter run fish hold in natal streams before spawning, whereas fall run fish spawn soon after entering natal streams, which means that we have different run types that can occur in the same area or the same stream. And so this is problematic for management, especially when we're talking about estimating entrainment loss of water export facilities. Next slide, please. So in response to this problem, several models have been developed to identify run. And so a length at date criteria were devised for run ID in 1989. And run ID is assigned based upon capture date and fork length, but there are 2 assumptions to this model. And then the first is that juvenile salmon from different runs hatch during distinct periods. And the second assumption is that juvenile salmon grow at a constant rate. So next slide, please. Okay, good. So Stevens in 1989 first plotted earliest and latest emergence time and average size of fish at emergence, and then extrapolated sizes based upon knowledge of juvenile growth rates. And there have been several iterations of length at date of this model to account for the 2 assumptions that I told you about in the previous slide and to improve the accuracy of run ID. So Fisher in 1992 recognized that a doubling of fish weight every month was unrealistic and instead used a growth rate estimated from juvenile fall run Chinook salmon reared in artificial spawning channels, so trying to approach a more normal growth rate. And next slide, please. However, there are still areas of ambiguity, mainly due to bi-monthly estimates of size ranges. And so you see here there on the right side under the Fisher model, there are these two lines, and those are areas where fish are essentially double classified. So, and the reason is because Fisher used only collected size range estimates at 2 points or 2 spans of the month, so every 14 days. And so, for example, a fish caught on December 14th that was 47 millimeters would be doubly classified as both spring and winter run. Next slide, please. And so, as I said, there have been several iterations of this model. And so the river model was an extension of the Fisher model that used daily intervals rather than those bi-monthly intervals. So there would be no ambiguities and no double classifications that were an artifact of those bi-monthly size range estimates. And so the river model has been used to designate Wren ID in the Sacramento River since 1992. Next slide, please. However, some coded wire tagged fall run fish were misclassified as winter run at the State Water Project salvage. And so in response to a request from the director of DWR, the Delta model replaced the river model in 1997 for fish sampled at the State Water Project and the Central Valley Project salvage facilities, as well as the Yola Bypass Fish Monitoring Program. And the main difference between the Delta model and the river model is that the Delta model includes modified upper and lower boundaries for winter run. So recognizes that growth rates for winter run in the Delta may be higher. And that size criteria from length frequency histograms for Chinook salmon sampled in the Delta for a long period were used to create the Delta model. So next slide, please. And length at date is still the primary method for Run ID and used for estimates of take. And it's really a valuable tool because it's easy to do in the field, it's easy to measure a fish in the field, but the approach is oversimplified. And so we still have this problem of overlap in fork length distributions among races, and inaccurate growth rates make length at date Run ID inaccurate. And so really now what we've been doing is turning to the use of diagnostic genetic markers to improve our Run ID accuracy, and particularly between spring and fall run Chinook salmon in the Central Valley. Next slide, please. And I'll speak more about genetics in just a moment, but just to give you an idea about how genetic analysis and length at date don't match. These are two figures. The left one shows, so in each bar on the left figure is a genetic classification, and then the gray dashed lines represent length at date classification. So on the left, you can see one of the really incongruent examples here is that many fish that are genetically fall run were classified as spring run. And I don't know if you can see my cursor, but see here, genetic ID fall run, but length at date were classified as spring run, which means that spring run were being overestimated. And similarly, in this figure here, you see each pie corresponds to assignment based upon length. So if you look at the spring run pie, genetic assignment are shown in colors, and so 95% of these spring run were genetically ID'd as fall run. So that's a pretty big discrepancy. And similarly for winter run, 59% were the same. So genetic ID matched with length ID, but then almost 50%, so 41% were either fall or late fall run. And so these overlap between fall and spring runs can lead to overestimation of spring and winter run fish, which is really problematic because these threatened and endangered species numbers could be lower than we think. Next slide, please.
Daphne, just to interject quickly, we cannot see your cursor, at least I can't, so you might need to just describe where you are or where you want to point. Go ahead.
Okay, thank you for that. Okay, so another model has been developed recently called probabilistic length at date, and it's under development. And this model relies upon fork length, sample date, and genetic identification. And the output of the model is a probability for each run assignment, and it may give more than one assignment per juvenile salmon. And so the probability is based upon genetic identification of catch from previous years, which is regularly updated. And so this particular model could be really important in identifying fish that have an ambiguous run ID from length at date that need to be set aside for genetic testing. So it could be this really complementary tool that helps us improve our genetic efficiencies. So next slide, please. So just a little background in genetics to those that are new to the subject. it's important to distinguish between genetic markers and then genetic methods. So genetic markers are a detectable segment of DNA that can be identified and tracked. And so these are really our points of variation that we use to track and identify individuals or species. And so you may have heard or may be intimately familiar with some of these kinds of genetic markers, which are allozymes, microsatellites, and then single nucleotide polymorphisms. Next slide, please. I'm really only going to be spending time talking about single nucleotide polymorphisms because this is the marker that the field is really moving towards. And so this is just a little figure of what a SNP might look like. So on the top, you have a segment of DNA, a sequence of DNA and from one individual, and then bottom is a sequence of DNA from a different individual. And you can see that all the base pairs, so these nucleotides, H's, T's, G's, and C's, are the building blocks of DNA. And the sequence between the top and the bottom, so those two individuals are the same in this particular region, except for one base pair difference here. So you can see the top individual, it has a C base, so a cytosine base, and the bottom has a thymine, so which is a different base. So that is a SNP, just a individual variation at one particular location. Next slide, please. And so then the genetic methods that we use to identify these particular genetic markers that are associated with a trait of interest or to assess genetic marker frequency among groups or populations are some of these, which you may have heard of before. So GT-seq, RAD-seq, RAPTURE, and a new technology called Sherlock, which is a CRISPR-based assay. And next slide, please. I'm going to be spending, I'm not going to be spending a lot of time talking about the first three methods, but I will spend a little bit of time talking about Sherlock. And the reason is because it has really important implications for identifying spring running and run ID in general. And it's a new technology that not many people are familiar with. So making sure that we all understand some of our options. Next slide, please. And so in the workshop, we won't really be talking about, which genetic method is best. Rather, we're likely going to be talking about our priorities that would help geneticists understand and kind of coalesce around which approach might be best. So we hopefully in the workshop we'll talk about things like what do we need in terms of what's our top priority? Is it turnaround time? Is it cost? Is it DNA quality? What's most important to us, and what's practical as we think about a tool for Run ID? Next slide, please. And so how do we arrive at genetic markers for Run ID? So what we do is we establish a genetic baseline from thousands of fish displaying our different run phenotypes, and then we look for those SNP differences between those groups. And then using that baseline, we can then genetically type unknown fish, so fish of unknown Run ID. And then, so based upon the state of the science in genetics, we've seen a strong association between the early migration phenotype, and then a region that's either within or between two genes, and those genes are GRUB1L and ROC1, and those are all, both on chromosome 28. And so we've seen fixed variants for spring and fall and late fall runs. And in California, heterozygotes typically are recorded as fall run. And just these two figures here on the top, you see the run timing distribution of Rogue River Chinook salmon genotyped at one SNP in the region of GRUB1L. And you can see that the homozygous spring have one phenotype, the homozygous fall have another kind of later, obviously migrating phenotype, and then those that are heterozygous kind of fall in the middle, so they have an intermediate phenotype. And then on the bottom, you see the proportion of individuals among the 4 runs in Central Valley Chinook salmon with heterozygous and homozygous phenotypes at one SNP in the region of GRUB1L. So you can see this pretty clear difference here so early migrating fish in spring and winter have one genotype, so two copies of the same SNP, and then late migrating fish have the other. So it's a very clear difference. Next slide, please. However, there are a few areas of caution when we talk about assigning run based upon genetics. And then the first is that the migration phenotype has not been standardized. And so anytime you associate a genetic marker with a phenotype, you have to make sure that your phenotype is well described. And so in this case, freshwater entry may be less noisy than upstream measurements. So trying to kind of coalesce around one phenotype. And then another area of caution is that causal variants for migration phenotypes have not been identified. So we have a lot of these SNPs that are highly associated, but it would be near impossible to do the kinds of experiments that we could say for sure, yes, this is the causal SNP. And also we may be overlooking other genomic regions of small effect. So we got really lucky in this case that migration, we had an area of large effect. So we had a few SNPs in one area that we were able to detect. Like, yes, this genomic region has an effect on migration timing. Whereas oftentimes you may have regions spread throughout the genome that are of small effect, so harder to detect. Another note is that heterozygotes can affect frequency of early migration alleles. And so this is particularly important when we're looking at interbreeding between formerly isolated spring and fall run in the Feather River that has made definitive run ID difficult. So again, likely as a result of heterozygotes with intermediate phenotypes. Next slide, please. So with higher than acceptable rates of misidentification and length at date, this is why we'd want to turn to a genetic ID. And so, however, the increased accuracy typically comes at the expense of needing increased time or molecular expertise. So it'd be great to have a genetic ID method that was not only accurate, but rapid, sensitive, and low cost. And so one possibility for this that is also currently being used for rapid COVID-19 testing is CRISPR-Cas9, and you can see the acronym there above, and it's gene editing technology. And however, Cas9 isn't the only CRISPR-associated protein that has been discovered, and different Cas proteins have different uses. So Cas13 is interesting because it has RNA-guided RNase activity that can be used to signal the presence of a particular nucleotide sequence, such as a diagnostic SNP for run ID. Next slide, please. And so one application of CRISPR-Cas13 is Sherlock. And so you see the acronym there, all these very clever names. And it was first developed in 2017 to detect Zika and dengue viruses in humans. And so I just kind of would like to run through the basic principles with you, which is the first thing that you need is a sample for your putative specimen of interest. And this could be any number of materials. It could be blood, it could be thin tissue, or mucus, or even eDNA. And so in our case, if we choose mucus, that we would have a swab that would be a non-invasive way to sample individual fish and get at run ID. And so recombinase polymerase amplification is used as an isothermal alternative to PCR, so polymerase chain reaction that we traditionally use to amplify DNA. So the entire reaction occurs at 37 degrees, and 37 degrees is also a temperature that you can achieve in the palm of your hand, which is great. And so it uses either RNA or DNA that's transcribed into RNA. And so if Cas13 finds its target sequence, it goes into overdrive cutting RNA, but not just your target RNA, but other RNA as well. And so that collateral cleavage can be used to our advantage by including an RNA reporter in the system that, once cleaved, gives off a fluorescent signal that only happens after the CRISPR detection of the target sequence occurs. And so Sherlock is specific, meaning that you can detect single nucleotide differences, so a single SNP. It's sensitive, so you can do single molecule detection. It's rapid, meaning that you can have results in about an hour, and it's low cost. And so each test is a few dollars. And so these same characteristics make Sherlock a great diagnostic tool for human diseases, and are also the same characteristics that we're looking for run ID. And proof of concept for this ecological application, or just application in ecology, has already been shown in previous work by Bearwald et al. In just this year in 2020. Next slide, please. So now I'd just like to show you how Sherlock works with a little bit more molecular detail as it relates to run ID. So again, you could take thin tissue or mucus from a swab that's, again, could be non-invasive directly, or you can use extracted DNA from Chinook salmon, which serves as a template for amplification and transcription to create amplified RNA. And so RNA, as you see here in the diagram, with the correct sequence is detected via the CRISPR-Cas system, and then reporter RNA is cleaved to produce a fluorescent signal. And so all of these steps happen in a single reaction tube kept at 37 degrees C, or again, in the palm of your hand at the same temperature. And so methods for field deployment are under development. Next slide, please. And so the high fluorescent signal intensity produced by the cleavage of this RNA reporter could be harnessed to a lateral flow assay for use in the field, much like a take-home pregnancy test. And these assays can detect the presence of a specific target by just dipping the strip into the finished Sherlock reaction. And so within minutes, if the test is positive, the sample band appears and can be seen with the naked eye. And so obviously these aren't, these plots down here just show fluorescence and how after just a few cycles, you can see a fluorescence difference between reporters that are associated with each of these different SNPs. And so to summarize, it's possible for us to differentiate spring from winter and fall, late fall runs and over a very short period of time. And so these modified Sherlock assays could enable genetic run identifications, which are 100% accurate, don't require DNA extraction, which means you don't need a genetics lab to perform this work, and can provide results extremely rapidly within 30 minutes and at minimal cost. So once developed, these field assays that actually use the strips that you see above, like akin to a pregnancy test, the cost would be even less than they are now. And so, yeah, with that, you can go to the next slide. I think we have the basic overview. And I'd just like to acknowledge all the people that contributed to both the fact sheet and also this presentation. And I know there are probably many others that are working on this. So thank you for your contributions. And yeah, we'll take questions a little later.
Great, thank you, Daphne. I would now like to introduce Adam Duarte, research wildlife biologist with USDA Forest Service and Oregon State University, who will be speaking on spring run life cycle modeling. And if you're looking for the fact sheet on this one, there isn't one. So we'll just be listening to Adam's presentation. Adam, you want to test your audio?
Yeah, can you hear me?
Yes,
Hello?
welcome.
Okay, deal. I am not looking at my presentation right now.
Just 1 second. Just grab it.
Yeah. No worries. Just making sure it wasn't.
Sounds like it's coming.
Yeah.
So anyways, today I'm going to talk to you guys about a project that Jim Peterson and I have been working on with the CVPA Science Integration team over the last 5 years. And I know this is a spring run centric workshop, but just bear with me. We're going to cover kind of Chinook in general, but know that most of the things that apply to these other runs, we're applying to Chinook spring run with some slight differences. So when we talk about the CVPIA Science Integration team, for those of you not in the know, or I guess who haven't heard of them, if you go to the next slide, please. The CVPI Science Integration team is a stakeholder group of volunteers from different agencies and organizations that meet pretty regularly to go through what's called the structured decision-making process. And their aim is really to go through and identify objectives, develop, evaluate, and refine decision support models, use those models to then evaluate trade-offs in different management actions in order to achieve objectives, in order to develop some science-based restoration strategies or policies. And this is part of the CVPI fisheries program. So we're talking about Chinook salmon of different runs, winter, spring, and fall, and hopefully late fall in the next couple of years. We're talking about sturgeon and omicus or steelhead. You go to the next slide. So today I'm going to talk about Chinook salmon, and in particular the model, because that's what I was asked to talk about. And so when we talk about developing models or life cycle models, you really have two options. You can go at it trying to do everything really, really well, or really, really okay, right? Where you're trying to leave the door open to really look at different scenarios or maybe look at different things. And although it's a good model because it does a lot of things, it doesn't really do a lot of things really, really well. Alternatively, you can build a model of purpose where it does a few things really well. And so that's what the SIT tried to do. Next slide. In particular, their model aimed to integrate knowledge from across the Central Valley. They wanted it to be course resolution. So what I mean by that is these models were designed to evaluate trade-offs in order to identify what to do and what area as far as what tributary. But we wanted to leave it up to local experts to identify where within a tributary to do some of this work because they're most familiar with the on-the-ground status of that area. We wanted it to track different key fish metrics at different scales. So the scales being at the tributary level or the Central Valley wide level, we wanted the model to be able to track adult escapement estimates, juvenile production estimates, population viability, and other metrics that I forgot to list here. And then they wanted to really get this model to evaluate management alternatives or sort of different management actions you could do in order to achieve your objectives. But more importantly, or just as importantly, to look at what sequence of actions over the next 20 years would give you your biggest push in fish numbers. And so different actions they wanted to look at were eliminate predator contact points. These are areas where predators are more likely to come into contact with your native fishes and potentially elevate predation levels. They wanted to reduce water diversions within the model, increase different amounts of habitat, so spawning, floodplain, and channel. Looks like I got something in my way here. No worries. Yeah, and then they also wanted to manipulate flows in the model in order to improve conditions and then remove barriers to open up access to different types of habitat. So next slide. So this next slide is just a conceptual model of the larger Chinook salmon model. This is the same for all 3 runs of Chinook. And essentially what we're looking at here is on the left side, we see hatchery on the top and natural origin adults on the bottom. And those individuals then spawn and deposit eggs. Those eggs incubate and juveniles emerge from that. So those juveniles have a couple different options in the model. What they can do is they can hopefully survive. Some of them are going to die. And if they survive, they can either grow or stay the same size. And then regardless of if they grow or not, they can choose to rear in the place that they're at, or they can move downstream. And so what this model does is it tracks those individuals from the natal tributaries down into the main stems of the Sacramento and San Joaquin, and then out through the Bay Delta, and then back again as adults. And if we're keeping count, there's 165 total parameters within each of these Chinook salmon models. Next slide. So a bit about the model structure, our spatial and temporal dimensions. Again, it's coarse resolution, so we're not looking at within tributary dynamics within this model. Instead, we're looking at treating each tributary as a unit. So we have 25 natal tributaries that are shown there on the left side of the screen in white. And then 13 regions. We broke up the delta into 13 different regions. So fish that spawn in these tributaries go through each of the main stems of the Sacramento. So there's 3 sections of Sacramento. There's one in the San Joaquin, out through the Bay Delta, and then back again on a monthly time step. Next slide. So given a model, outputs are always tied to what the inputs are. It's worth pointing out what our model inputs are for the science integration team's DSMs, or decision support models. Next slide. We have different types of habitat, flow metrics, temperature, of course, fish parameters, and fish numbers. Where we use measured values from different monitoring programs throughout the Central Valley. Where we couldn't do that, there's some pretty awesome models that are already in place to look at flow, or maybe some temperature models and habitat models. And then in small cases for habitat, there really wasn't any information. And so we ended up relying on expert elicitation just to get at roughly how much habitat was in some of these tributaries. And it's worth pointing out that these inputs were used to both run the model for inputs, but then things like the Grand Tab or fish abundance estimates were used to calibrate the models in order to make sure that we were kind of matching the hatch, or matching what we're seeing in the real system. Because as Flora pointed out, we were missing a lot of information on survival, so there was a little bit of model calibration in there for that. And we'll come back to that in a second. So next slide. So we had 3 Chinook salmon runs within these DSMs. I'll focus in on spring run here, but essentially in the model, spring run will spawn in September and October. And of course, eggs incubate through November. Those juveniles emerge. And that's when they start kind of holding and rearing or moving through the system. And then in May is when juveniles then opt to follow a yearling life history strategy, where they'll hold until the following November, until they leave the Bay Delta, or they just continue to move through the system and leave that May. Next slide. So that was a lot I kind of threw at you just to kind of point out this is sort of behind the scenes what's in these models. And it's worth pointing out that the point of developing these things was to help focus the discussion. We wanted to be able to simulate every combination of actions in each tributary, as well as the main stem sections, to find some sort of what to do, where, and what sequence of actions mattered. From like a modeling standpoint, that's really easy to do. I mean, it's just a for loop I go through, and it takes 20 minutes to set up. But let's think about this for a second. If we assume there's only 4 potential actions per tributary, and we want to look at a sequence of actions over 20 years, that ends up being an exponentially large number of scenarios that I don't think any of us have enough time to sit here and wait on the computer to do. So we needed to find another way, a more efficient way. And so if you go to the next slide, the objectives really were to use these models, but to develop an efficient approach to evaluate all combinations of actions, including the sequence of actions, to evaluate these alternative strategies or management actions across Chinook runs in order to identify science-based priorities for both actions as well as information needs. And so in order to do that, we really kind of had to pick the model apart. If you go to the next slide, what we ended up doing is we started looking at the model at 2 different levels, right? There's the Central Valley wide scale, but then there's also the tributary level. And when we think about applying restoration actions to a tributary, what we're talking about is a Markov decision process. And a Markov decision process is a really fancy way of saying something that we all do every day. Basically, you go out, you look at your population state or the conditions that you're in right now. You can look at a set of management alternatives, evaluate which one you think is best. You then make a decision, you implement that population state for the next time step, and you do it again, right? So if you're doing a management action, you evaluate fish numbers, you evaluate where you are, you make a decision, you change fish numbers. It's just a repetitive idea of looking up where you are to decide where you want to be. And this is important because there's awesome optimization procedures that have been developed in the computer science field in order to solve Markov decision processes. So that's what we're going to do for within a tributary. Next slide. The problem with these awesome optimization procedures is that they're really complicated, and you can go into what's called a curse of dimensionality, where you just have too much things to look at. So you really need to start focusing on what really matters in order to use these tools. And for the Central Valley Science Integration team, there was 2 main objectives within a tributary that they were concerned with. They wanted to push as many juveniles out of a tributary, which makes sense, into the ocean, so hopefully they return, but they also wanted to maximize the number of adult returns. The reason why there's this trade-off is that for juveniles, whenever you do an action, you can see immediate returns on that, right? If I create habitat that year, potentially I can see my return on investment that year if I follow the juvenile metric. However, with for adult fish, you'd have to wait 3 to 5 years. And then some things are outside of your control, like ocean conditions. But as hard as that is to kind of grapple within the real world, within a modeling framework, it's actually really easy just to send those juveniles out to the ocean and track the number of adults that came back for that cohort. And so we're calling those adult equivalents, and that's what we maximized within the modeling framework. Next slide. And when we talk about all the different actions the SIT wanted to evaluate, it really came down to 4 things that we were actually manipulating within the decision support models for Chinook salmon. We were creating habitat of different amounts, or we were trying to increase, so creating habitat either by some sort of action or removing a barrier, or we were trying to increase survival through manipulating flows and temperatures or removing predator contact points or anything else. So those are the 4 actions we focused on. And then we had to know how much habitat or how much increase in survival we were going to let the model implement. And so to do that, we looked at the past CVPA fisheries program projects. And what we noticed is there's a wide range in costs associated with the project, but relatively little variation in the amount of habitat that's created for most projects. So for most projects, when they go out and create spawning habitat, they're roughly creating 1 acre. In channel rearing habitat, they're roughly creating 2 acres per project. Of course, there's some variability with that, right? Sometimes you go out and you create half an acre. Sometimes you go out and you do a great job and you get 1.5 acres. This was called partial controllability, so that uncertainty with if I go out to create spawning habitat, there's going to be some variation in how much I actually create. But these optimization procedures include that variation, and this is called partial controllability. And so we were able to include that uncertainty within our modeling framework. Next slide. And then we had to figure out what state variables, what population state variables we wanted to monitor. So what do you need to look at in order to evaluate what you want to do? Based off previous model runs, again, we've been working this for 5 years. So the past 4.5 years, we found there was 4 things that always influence what you would do in a particular tributary. So again, within a tributary, the amount of in-channel rearing habitat, the amount of spawning habitat, the number of fish that were using it. So those are the number of spawners or reds, and survival for rearing juveniles within a tributary. So those are state variables. So next slide. So what we can do is we could take that information and we can use optimization procedures to solve the model at the tributary level. And that sounds great, except for the fact that we know each of these tributaries isn't the same. For example, fish that leave Clear Creek in the northern part of the Sacramento River have a lot further to travel down out to the Bay Delta and back than fish that are in the American River or the Cosumnes. So we wanted to incorporate that geographic variability. But even within that, if you go to the next slide, we see that some of these tributaries are, even though they're in the same region, act differently. Some of them, based on flows and how fish use habitats, have slightly increasing habitat throughout a juvenile rearing and movement window. Some of them are slightly decreasing, and some are pretty stable. So what this meant is we had to solve the model at the tributary level for 6 different groups. So we had to do it 6 different times. Next slide. And we did that by relying on the CVPI Science Integration Team's decision support models. So essentially what we did was we used those models within a tributary to develop every combination of here's where I am, if I did these things, here's what I would be. And that creates what's called transition probability matrices. And you can then feed that into an optimization procedure called stochastic dynamic programming in order to derive a set of optimal policies in an infinite time horizon. So what you get out of that is what's called a policy plot, but you can think about them as lookup tables. They're shown there on the right. So if you go to the next slide, I circled some things on it. So essentially what you're doing here is you're using the axes to figure out where you are. So if you know how much spawning habitat or juvenile rearing habitat you have, you know how many reds over the last 5 years on average we're using that area. Sorry, saw something in chat there. And if you roughly know how the juvenile rearing survival is within that tributary, you can just figure out what the optimal decision would be within that tributary. So if you have lots of spawning habitat per red and not that much juvenile rearing habitat per red, you'd be in the bottom right of that box. And the optimal action would be that dark gray color, which is, in this case, adding rearing habitat. But if you had lots of habitat of both kinds, you'd actually be in that black area there. So black box is where you wouldn't create habitat at all. Instead, you would focus on increasing survival. So next slide. So we, again, did this for solve the model for each of these different groups. And then here I'm showing you one policy plot per group, but there's actually 10 policy plots based off the different number of juvenile survival estimates. And you can use this going forward. So next slide. How do you use it? Well, if you're a manager and you work on a particular tributary and you have a lot of faith in the science integration team's models, you can just use it and say, well, here's where I am with my particular tributary. Here's what I should do over the next however many years it takes to complete a project. But within a modeling framework to identify priorities, you can actually use them as lookup tables so that when you're simulating population dynamics forward, you can apply optimal policies based off where the simulated fish numbers are. And so that's what we did. So the science integration team wanted to simulate 20 years of actions. They wanted to force the model to only choose. So we solved the model tributary level. Now we're looking at Central Valley wide. So they wanted to only allow it to pick 5 actions across the Central Valley implemented per year. And this was based on roughly the on average number of new projects the CVPIA fisheries program implements each year. And they wanted to evaluate alternative strategies in order to boost adult equivalents for different Chinook salmon runs. So next slide. You're not meant to read any of these scenarios or strategies, but essentially what we're looking at here is 14 different strategies they evaluated, Strategy 0 is your no action. So that's your baseline, right? This is doing nothing. How do the fish numbers do? Strategies 1 through 7 were based on previous model runs where essentially people came up with their best strategy that they would put forward just to see how it would play out in the models. Strategy 8 is where we relied on those output from stochastic dynamic programming in order to optimize actions for winter run Chinook salmon. Strategy 9 and 10 was using stochastic dynamic programming, but here we're forcing the model to work in only certain locations, but picking the optimal actions. And the same thing for strategies 11 through 13, only it was fall run centric. So what do you get out of this? If you go to the next slide, here's an example from fall run where we essentially just wanted to maximize pick actions and it'll attribute to maximize fish returns. In this case, you see where the model picked to work. We see that the model picked what action to do. And we see that in some cases, what you would do in a tributary switched on and off with something else. So it's giving those sequence of actions. And we got this for each of those scenarios for each of the 3 Chinook runs. Next slide. The other thing you get out of this is you can get predicted natural adult production. So here, that yellow, each of these lines represents a different strategy across the 20 years, those fish numbers. So that yellow line that I'm pointing at that you can't see is the one that optimized actions for spring run. So it's no surprise here that when you pick actions that optimize fish numbers for spring run, you end up with more spring run. That's what we're showing here. Next slide. But perhaps what you're most interested in when you're looking at the central value-wide level for different anadromous fish species is how do you prioritize things across runs, in this case for Chinook salmon. And so what we did is we looked at the relative utility or the relative fish numbers gains based off these different strategies shown here on the x-axis. So the black lines here, black bars represent fall run, gray bars are winter run, the white is spring run. We see again that scenario 9, strategy 9, the one that optimized spring run, was best for spring run. But the scenario 6 was best for fall and winter. If you go, and the reason why we looked at relative utility is worth pointing out is because the numbers of fish in each of these runs is just so different that looking at total numbers didn't make a whole lot of sense. It was hard to really digest. If you go to the next slide, what we ended up wanting to do is say, well, is there some sort of combined utility, some sort of combined gain that we can get out of this, some sort of scoring? And so when you weight each of these Chinook salmon runs equally, we see the most optimal scenario of strategy was strategy 6. And if you do weight them multiplicatively, where you're forcing the model to, so you're forcing these things to never pick the worst scenario for a particular run, we see that the optimal scenario strategy is still strategy 6. So if you go to the next slide, so the thing is we know strategy 6 seems to be the best when you combine across runs, but we also know that strategy 9 was best for spring run. And so the question is when would I choose when would I choose strategy 9? When would strategy 9 be my most optimal thing to do? And so what you can do is use proportional scoring. So here's a slide. Essentially what we're doing is we're messing with how we weight the different runs, where the weights of the different runs all sum to 1. Originally we were looking at 0.33, right, or 0.3333. So everything sums to 1. But if you start weighting spring run more than the other runs, we see that strategy 9, which is, sorry, what I should point out is these are different strategies. The top strategy on the line, on the axis, is the optimal one. So as you weight spring run more, strategy 9 becomes the dominant strategy that you would want to do. How much more? Well, you have to weight it over 0.5. What this means is you'd have to value spring run twice as much as winter run or fall run in order for strategy 9 to be considered your optimal strategy across Chinook salmon runs. Next slide. The other thing you could do is play games with your model, right? You can go through those 165 parameters plus all the model inputs and make things, there's some uncertainty associated with them, so just mess with the values. Go through and make things really, really small, make things really, really big, and then look at what the optimal action or strategy would be. And so that's what we're looking at here. Here's an example from fall run, where again, the line on the top is your optimal strategy. the box on the bottom is where most of your parameters are going to fall, where things are parallel. What this means is no matter what uncertainty I apply to a particular parameter or model input, the same strategy ends up being optimal. But there are a handful of parameters in which the model is very sensitive to, and that's what's shown here on the top, where if I increase the uncertainty in something, another strategy may come up as better. And so what this means is these are key uncertainties that you would want to resolve in order to make better decisions moving forward. So next slide. And if we looked at that across all the 165 parameters and all of the model inputs for all 3 Chinook runs, we saw the same patterns kind of emerge. We saw for common top uncertainties for model parameters were those juvenile parameters, survival and growth, reproduction, adult survival, and then juvenile territory size. And for model inputs, it makes sense that when you're trying to evaluate where to make habitat, the amount of habitat that you have in these streams from the get-go is influencing whether you would create habitat there. It's worth pointing out that both of these uncertainties are reducible. Juvenile metrics can be reducible through focused monitoring effort, and model inputs are updated every other year. The science integration team has every year has annual watershed expert meetings where we go and meet with the watershed experts, folks who work on these different places, in order to ensure that the model is capturing that system as best as we can. It's also worth pointing out that both of these uncertainties, or sets of uncertainties, were pushed forward by the science integration team as priority information needs. Next slide. So conclusion, the science integration team was able to go through the structured decision-making process and use decision analysis in order to focus on what really matters and develop state-dependent policies. These state-dependent policies using stochastic dynamic programming are equivalent to the evaluation of every combination of actions and sequence of actions. But the benefit is it includes stochasticity and includes that partial controllability, where we go out and do an action and there's some variability with the actual result as far as how much habitat we created. We found that decision analysis simplified the problem and really focused the discussion so that SIT could focus on things that mattered and separate those that didn't really matter within a modeling context. And from that, they were able to identify restoration priorities and identify information that is needed to make informed decisions and better decisions moving forward. So I know I kind of ran through a whole mess of stuff, and I'm glazed over a lot here, but if you're more interested, even though I don't have a handout or a pamphlet, if you're more interested in the modeling aspects of this, Jim and I just published a paper in Restoration Ecology. It's available online now. We're currently working with the journal to make it open access. So if you don't have access just yet, just hopefully within the next month. If you're more interested in the people process and what the priorities were sent up to the implementing agencies from the science integration team and how they use this information to develop a restoration strategy, I'd point you towards the near-term restoration strategy that should be released within the next month or two. Next slide. And with that, I'd like to thank a lot of folks, in particular the CVPI science integration team. I mean, I'm sitting here presenting this work, but really this is the product of a group of stakeholders who volunteered their time over the last 5 years in order to come up with science-based priorities for the CVPI fisheries program. And I think we're taking questions later. But that's all I have.
That's right, Adam. Thank you very much.
Yep.
Thank you so much. I do want to introduce now Peter Nelson, a senior environmental scientist with Department of Water Resources, and he will be talking about the juvenile production estimate approaches. And that does have a background document called the JPE approaches fact sheet. So I'm going to hand it over to Peter.
Thank you, Julie, and thanks to all of you for participating in this workshop. This is an exciting opportunity. Hopefully you haven't all been too frightened off by the complexity and the scale of the task ahead, but it should be, I think it's going to be interesting stuff, and it's going to be fun. So what I'd like to do this morning is give you a preview of what a JPE looks like, what a juvenile production estimate model looks like. You know, some of the components. I'll talk a little bit about the importance and something, a little bit about the challenges. So this is really intended to be sort of preparatory or a setup for the upcoming breakout sessions tomorrow and the day after. And it's all sort of geared towards the development of a plan for how we put together a spring run JPE. So I'm not going to consider all the various factors or ramifications. In fact, the talks that you've just heard really provide a fantastic introduction to some of the many different factors that go into this. So if I could have the next slide, Brandon. So what exactly is a JPE and why do we have to have one? Some of this has been touched on already, but to reiterate, a juvenile production estimate is an annual forecast of the natural origin spring run juvenile Chinook salmon that enter the Sacramento-San Joaquin Delta. And the most proximate reason we need to have a JPE is that this is necessary. This allows or determines the
Peter, this is Julie Lineback. We just lost your audio. Maybe we could turn your audio on and off again and see if we can get you back. Brandon, this is Julie. Can you hear me?
Yeah, I can hear you. I'm checking out and seeing if he's on mute or not.
Okay. Great.
He isn't muted.
Okay.
So I don't know if maybe he lost his connection. He is still on though.
Let's see, Peter, if you would like. Oh, there you are.
Okay. I unplugged and plugged my mic back in, so hopefully it'll stick with us.
Thank you.
Okay.
Great.
Sorry about that. All right.
No problem.
So I wanted to point out that in addition to sort of the necessity for a JPE, in that it's required by the incidental take permit, we get a number of really important additional benefits. So number one, it's going to provide a critical bit of information to greater understanding of spring run biology and ecology. This is directly relevant to, as others have mentioned, to the recovery of this listed species. This can contribute as well to sort of fisheries management. This is an ESU that forms at least a part of a critically important commercial and sport fishery here in California and further up the West Coast. And finally, this JPE helps document the potential impacts of changing environmental conditions. So all of these, in addition to sort of this proximate legalistic necessity, a JPE can contribute to a number of important efforts. Next slide, please. So what does production mean in this sense? So we've already seen or some discussion about sort of the basic salmon life history, beginning with egg production. Those eggs hatch as alevines. Those alevines emerge from the gravel as fry. They develop into smolts. Smolts migrate out to the ocean. Adults from the ocean eventually return to freshwater habitats as spawners. The point that I want to make is there's basically two. One is that this process occurs in the context of multiple very, very complicated systems. Everything from these relatively high elevation freshwater streams through large rivers down into estuarine habitats and out into the ocean. It's But in addition, this process is further complicated by human activities as well. In the Central Valley, perhaps the most obvious being agriculture. So while humans impact Central Valley Chinook throughout this life cycle, so in addition to sort of this happening in sort of this complex environment, we're going to focus this JPE discussion and our efforts to sort of understand juvenile production on a relatively small portion of this salmon-like life cycle. So in the diagram on the left, you'll see that out of that entire donut, there's a relatively small bite there highlighted in red, covering from, basically fry to smolt. That is likely to be the area of the life cycle that we emphasize in developing this JPE. Nonetheless, every single one of these stages is dependent upon the previous stage. So the effects of survival across this entire life cycle has major implications on our forecast estimates. But again, for the purposes of the JPE, production is measured at the point where juvenile salmon enter the delta. Okay, next slide, please. Now, the elements of a JPE are going to rely on spring run life history. They're going to rely heavily on accurate run identification, and they're going to rely on some of these key data streams. At the very minimum, you might expect that a juvenile production estimate is going to incorporate some initial forecast of juvenile production, perhaps up in the upper river in some of these Sacramento River tributaries. But then that is going to be modified by survival, by the survival rate of those juveniles as they wend their way from these tributaries down to the delta. The combination of those two things at a minimum is going to give you some estimate of the juvenile production. So I've tried to illustrate this here by showing you in the lower left there, you see, some rotary screw traps. So this is one method. Flora went over many of these juvenile monitoring programs, but it's just one way in which you might develop an initial estimate of juvenile production. The quartet of images on the right show the surgical implantation of acoustic tags. So the point being that we do have technology that allows us to track juvenile salmon even at a relatively small age, very small age, through this system, and thereby estimate their survival probability over the course of that migration. The photos illustrate coho salmon, but it'll do for the purposes. Next slide. Now, despite the simplicity really of that previous model for a JPE, there's a whole host of different modifiers. So again, the prior talks have really given you a tremendous introduction to the diversity of these potential modifiers, these factors that could potentially be incorporated into a JPE. Everything from the number of spawning adults, egg production, quantity and availability of spawning habitat, and so on, up to and including, various measurements of error or uncertainty. This is nicely illustrated by the map that Flora made for us, that you see in the middle here. It shows sort of the spatial diversity of spring run spawning habitats. All of this then is compounded by a slew of different challenges. Run identification, you heard lots about the details of that from Daphne earlier. but you've also got the potential role of hatcheries and experimental sources. You've got the amazing life history variability. Life history variability and diversity certainly works to this run's evolutionary advantage, but it makes development of a JPE much more interesting, shall we say. Adam mentioned he's had 165 different parameters in his model. I assure you that we don't want to try to incorporate all of those in a JPE, but again, it sort of illustrates the potential complexity and the challenges that we're facing here. Next slide. So one of the things that I wanted to do in this talk was to outline some of the winter run JPE models that are currently or have been used as a way of illustrating how we might approach a spring run, the development of a spring run JPE. So here, this table shows, again, a comparatively simple model incorporating across the top, the number of spawning adult fish, the estimated viable eggs per adult, the survival of those fish as they move from spawning habitat and cross RBDD, that's the Red Bluff Diversion Dam. And from those initial estimates, you can get sort of that initial juvenile production, the so-called JPI or juvenile production index. This then is modified by an estimate for the survival of these fish as they go from the Red Bluff Diversion Dam down the main stem Sacramento River to the delta, and ultimately resulting in an estimate of the number of juveniles that reach that delta, the JPE, on the column on the furthest right. So I've included this to sort of show a relatively simple approach to a JPE, but also to illustrate how different estimates in particular impact that ultimate forecast. So, again, focusing on the column there on the right-hand side, you can see each of those lines result in significantly different numbers of the juveniles that are projected to reach the estimate. So it behooves us to have the best possible monitoring data and, the most informed estimates of survival as we develop this JPE. Next slide, please. Now, in addition, sort of more recent advances in modeling these kinds of population estimates have now allow us to incorporate a number of different measurements of potential error or variability. So Michael Farrell in particular has looked at 3 different alternatives for sort of measuring or estimating winter run juvenile production. These numbers here are taken from his 2018 paper, where they compared these different 3 alternative JPEs, and they differ essentially, basically, in terms of how they account for error. So method number 1, the method on the left, basically doesn't include any error estimation. Method number 2 accounts for observation error. Observation error being sort of the variation that's sort of intrinsic to the methods used for these counts or population estimates. This might include, certainly any forms of human error in RED surveys, or the difficulty in detecting fish picked up in a rotary screw trap. Then the third method, the furthest one on the right, rather, includes not just observation error, but also process error. So process error, you might think of as being the variation in the true population size, due to, a whole host of various biotic or abiotic processes. These are basically the real drivers of population fluctuation. So the benefit of including these techniques for accounting for error is that really it gives you greater confidence in your model output. You might counter that by arguing, well, look at the ultimate JPE that's produced by these different methods. We get less fish if we account for error. Yes, perhaps so, but more importantly, we can then have potentially greater confidence in those outcomes. Next slide, please. So I'm not going to go through these questions that we've come up with. We'll go through them and many more, I'm sure, in the days to follow. But I hope that I've given you a sense for what the task at hand, and I hope that you're convinced that this is both an important and an exciting project. It's going to require the collaboration of obviously of multiple agencies and multiple scientists, all of you. And I want to thank you again for participating, and I'm really looking forward to working with you. Thanks very much. Next slide, please. And that's it. I guess.
Thank you.
Questions to follow.
Yeah. Thank you, Peter. I appreciate it. Thanks for that, pulling it all together for us into the JPE. I now am going to open up our question and answer discussion. And I already did have a question from Brad Cavallo from Kramer Fish Sciences. So Brad, you're in the queue. I just want to remind everybody, if you put your name and your affiliation in the chat, then I can get you in the queue. We're not using the hand raise function because some folks don't have that function. So go ahead and do that. And Brad, you're up.
Hey, thanks, Julie. So my question's for Daphne. So my understanding is that the SNPs that are associated with the OTS region, not a geneticist, forgive me, those SNPs allow us to pretty effectively distinguish spring run from fall run. Is that accurate?
I would say that's accurate, yes.
Okay. So then there's a variety of analytical methods that might be used to find out what those SNPs are to make that determination. But there's a bunch of different methods you could use, and we might have a discussion about which one we do, but CRISPR isn't the only one that can yield that data. It's one methodology, and there's other methodologies that could also provide that SNP data. Is that accurate?
Yeah, that's accurate, and that's what I was saying on that slide when I talked about there's GTC, there's Rapture, there's a bunch of different methods, but I thought that it was really important to also highlight CRISPR and Sherlock just because it's new to us, and I think a lot of people aren't familiar. So making sure that we all kind of are educated about that too, since it's so new.
Okay, I think it's really valuable for everybody to know that we actually can genetically distinguish spring run for fall run, because that's been a sticky issue for a long time. Thanks.
Yeah, agree.
Thank you, Brad and Daphne. Let's see, in the chat, I am looking here, but I don't see any new folks who would like to make any questions or comments. Let me just give you a few minutes here to find the chat button. It looks like Bruce Herbold. Would you like to unmute yourself and go ahead with your question or comment?
Yeah, on the decision support models, is there any way to put in the fact that some of those actions take a lot longer than others, or ways to put in that in a particular year your priorities might shift?
Yeah. So I'm assuming that's me, but certainly you can. What's nice about the modeling framework is it's kind of dealer's choice. If you have a scenario that you would like to evaluate, if you can describe it to whoever's programming it, it's a relatively easy thing to incorporate. That's actually one of the things we're talking about with the science integration team too, is really trying to get these models to a place that we think they're in a good spot, and then start exploring them and seeing if we can push them in sort of these random directions.
But you haven't put in the fact that some of those actions take a lot longer than others as a
No,
decision.
no, right now it's sort of an instantaneous, here's 1 acre this year, here's 2 acres this year. And yeah, so we're looking at a best case scenario, but it's important to remember that when we're looking at cross runs, we're looking at the relative benefits of these things, right? And so we're being optimistic the same way across these different Chinook salmon runs.
Cool, thank you.
Yep.
Thanks, Bruce. Thanks, Adam. Anybody else? Just to remind you, these question and answers are on all 3 of our presentations after the break. So we had Daphne Gill talking about tools for spring run identification, Adam Duarte talking about spring run life cycle modeling, and Peter Nelson just now talking about juvenile production estimate approaches. And feel free to just put your name and affiliation into the chat. And Brad, it looks like you have another question. Go ahead and unmute yourself.
Okay, thanks. Hey, forgive me if this is coming up in a subsequent day, but so the purpose of the Spring Run JPE, as I understand it, is to help inform entrainment loss monitoring. There's some information available about entrainment loss of Spring Run Chinook. Has that information been considered? I mean, it just seems like that might be another really good approach to this, would be to start with the loss that you're concerned about, like how much loss is what you're concerned about, where do you want to set your triggers, and then kind of plan backwards from that. Like, okay, if we want to keep loss below this certain level, then we need to have an estimate of spring run coming into the Sacramento River that has a precision of X. And then the other issue is that Rachel mentioned in her presentation that we have spring run in the Stanislaus River. Those fish are much more likely to show up at the salvage facilities than Sacramento Basin fish, just because a lot of them are going to pass right by there. So there's just a couple of considerations that seem really important for using this as sort of a management tool for entrainment loss.
Yeah, I think that's a great point. Both of those are great points, Brad. And I think, I mean, not to duck the question, but I think essentially those are both ones that absolutely should be considered in our, in our breakout sessions. Just sort of what the trade-offs are between, which of these factors we incorporate. But I don't think there's any question that some of the historical stuff, near term and long term, needs to be considered in developing this model.
Great, thanks for that. It looks like we have another person here. Barb Byrne, would you like to unmute yourself and go ahead?
Julie, this is Barb. I just wanted to second Brad's point. I think we have great news of fish in the San Joaquin Basin, but it does make for some complications, both in the Sac Basin JPE, and also because the San Joaquin River Restoration Project has a commitment for de minimis effects on export. So it's just something to keep in mind, as Peter said. Good topic for discussion tomorrow. We need when it comes to developing a Delta performance metric, we have to consider those San Joaquin Basin complications.
Great, thank you. Just follow-up question on that, Barb. Is there any information that you would like to see in relation to that to support your discussion beyond what's in the fact sheets?
I don't need any additional information. If folks are interested in that sort of de minimis effect issue, I can go to our San Joaquin Restoration Program experts and pass that along. But I don't personally need it, but I can pass it along if others want it.
Thanks, appreciate that. I have Steve Zug from Kramer Fisheries on deck here for the next comment, and if anybody else wants to just join the queue, feel free to put your name and affiliation in the chat. Go ahead, Steve.
Thanks, Julie, and thanks everyone for the presentations. It's very informative. Riffing off of what Barb and Brad were talking about, and it came up in Rachel's presentation, is this issue of like kind of confounding fish. So like those Yuba River spring run, their abundance is not counted towards recovery as included in the 5-year assessment, but those fish arriving at the salvage facilities or down in the Delta would still be identified as spring run and counted as take. So I don't know if there's been any consideration of how you differentiate effects of these spring run populations that don't count towards recovery versus the ones that are part of the Core 1 systems.
Steve, I wonder if there's somebody in particular from the 3 last panelists that you'd like to direct that question to?
I would say probably the person working on the JPE. I forgot his name.
Yeah, that's
Peter Nelson.
That's
Great.
me, Pete Nelson. Sure, Steve. No, again, that is a super good point, and definitely something that we need to consider. I mean, one factor I think is likely to be, of course, our ability to distinguish, some of these fish coming out of the Yuba versus fish that may have originated elsewhere. So it's one of the downsides, I suppose, to having our breakout groups split up by run identification and JPE development and monitoring efforts and things like that. Ultimately, we're going to have to bring it all together. But I would say, yeah, let's wrestle with that. Let's in particular, we need to work with both folks involved in monitoring these juvenile fish in obviously coming out of multiple systems, and the folks who can help us identify or distinguish among them.
Steve, do you have any follow-up there or any suggestions about how to address the issue that you just brought up?
Well, I'm not sure about how you address it in a JPE, except for treating all those fish the same. Since they're all treated the same when they arrive at the facilities, that just means to me that you have to consider every single tributary and maybe not just the Core 1 tributaries. But if that's going to be the case, then we might also need to focus some effort on how to get those Core 2s to Core 1s. Otherwise, what we're getting in terms of the JPE may not reflect the performance of the population as it's evaluated in the 5-year status review, since those Yuba and featherfish aren't counting.
Great, thank you. Peter, any other thoughts on that?
Well, I mean, I could speculate, I suppose, on a range of possibilities. So if we're able to determine that, of the fish that appear in those salvage facilities, only a negligible number are coming from Feather River or Yuba systems, then arguably, maybe it doesn't matter. Maybe it falls within the margin of error for that JPE. On the other hand, we're going to have to figure out if in fact that's the case. Theoretically, we should be able to weight the contribution of different systems to that total JPE. But again, it comes down to the effectiveness of our monitoring and our confidence in in the numbers that we're getting. So I certainly don't have a solution off the top of my head, but that's why we're bringing folks together here and working on trying to develop a solution or a way to deal with that very real challenge.
Great, thank you, Pete.
Thanks.
Thanks, Steve. That seems like a good point to close our discussion for now. Obviously, we will be in breakouts tomorrow having quite in-depth discussions, and I hope that this morning has set us all up to do that. We're going to do one more Mentimeter digital poll here, and so if you reopen your browsers, Brandon is going to, I think, put up the instructions again for the Mentimeter. It's menti.com, and you enter the code 8687434. And we are going to have a few last questions. There's 2 last questions. What's the most important thing that you learned today that you didn't know before? And then coming up in the queue will be, what are the key questions or issues you're looking to unpack during tomorrow's breakout session? So for those of you, we would really love to know, what is the most important thing that you learned today? What was new? And then, of course, we'll want to know a little bit more about your key questions for tomorrow. So these are going to come up in a slightly different format than we did before. They're going to be little notes that come up on your screen. And so as they populate, they'll just scroll right through and we'll have documentation of what people have brought up here. It looks like just pulling out some highlights. It looks like a few people have said Sherlock, that was new for them and they appreciated learning about that. Other ways of saying that actually are about genetic advances. So Sherlock, genetic advances seem to be common responses. Let's see, spring run having unique adaptive capacity compared to other salmon, and very, very relevant, the basic components of a JPE. Looks like others, again, harking back to the genetic differences and the CRISPR tool. So that Sherlock CRISPR piece sounded like it was really helpful and very new for folks. And it sounds like it will contribute to a rich discussion tomorrow. I'm seeing also results from the SIT model that Adam presented. Spring run modeling. Okay, the accuracy about length at date metrics. I'm just picking out a few here, but you can see if you're looking at the browser that folks are responding here, and it's some of them have quite a bit of detail, which is nice for us to get a sense of what was new here, and it seems like what might need to be unpacked a little bit tomorrow. Great, thanks everybody. That's very helpful, and it sounds like there was definitely some new information presented today that could be very helpful for your conversations tomorrow. Let's go into the conversations for tomorrow with this next question. What are the key questions or issues you're looking to unpack during tomorrow's breakout session? So again, we're on menti.com. It looks like many people are participating, but I'm going to just give you the code again, 8687434. And this will populate in the same way that the last one did. So for tomorrow, key issues, things people want to unpack. How can we improve monitoring? Handling Yuba feather fish in the JPE. Monitoring is repeated a few times. Generally, people are talking about JPE approaches. There are some very specific questions people have, which we'll see if we can get those to the breakout facilitators before the breakouts. But please, jot this down yourself. If you have this question, bring it up in the breakouts tomorrow. So I'm seeing specific things like egg survival estimates, links to entrainment. Let's see, pick out a few more before it scrolls away from me. Big questions like, faced with trade-offs between scientific objectives, what absolutely needs to be achieved and what could be delayed or modified? So a sequencing question. What are the best ways to put JPEs into management for spring run that has different out-migrant strategies in different years? Okay, and maybe some more specificity about the use of video monitoring on the Feather River, and various ways to account for uncertainty in a JPE approach. Great, this is very helpful, everybody, and I hope it's helpful for you too, just coming out of the end of this day to just jot down a few things that you would like to cover in the breakout sessions tomorrow. And again, we'll share this with our breakout group leaders. So I want to thank everybody for keep populating. Go ahead, you can keep going with that. I do want to ask Brandon to just move the slide that you're sharing to the wrap-up slides, just so that I can go over with folks to give them a taste of what's going to happen tomorrow. Give you a little bit of a map for what you'll be doing. So I know Brandon's working on getting that up, but just to describe the breakout groups, there'll be 30 participants in each breakout group. It sounds like some of you may be assigned your second choice rather than your first choice. Thanks for your patience with that. Participants in the breakout groups will respond to 3 questions that are listed on the day 2 agenda. So you can find those. And if time permits, you also may address questions on the respective fact sheets. Some of the presenters noted their questions in the presentations. If you've taken a look at those fact sheets, they have maybe 4 or 5, sometimes 6 other questions that are pertinent to those issues. I'll also add that there will be a facilitator and a note taker for each breakout, and they are provided by Delta Stewardship Council, Department of Water Resources, CDFW, USBR, and PSMFC. And then all your great work that you're going to do together tomorrow in the breakout, the note takers and the facilitators will work to summarize and synthesize that and present it, report out, right, on day 3. And that way you can hear what the other groups have discussed. So, and then that summary will also be included in the workshop meeting summary. And of course, as Ted and Louise mentioned earlier, this is all fodder for developing their JPE approach and for the article that will be produced. I want to say, just if you have questions about the breakout groups, I want you to email Eva Bush with the Delta Stewardship Council. It's eva.bush@deltacouncil.ca.gov. So all this information about the breakouts, if you're wondering, how do I get there? How do I get the link? It should be in an Outlook calendar invitation that was sent to you and in an email with breakout group materials. But if you can't find that, and please contact Eva Bush to be able to access your breakout group. I think that is it for tomorrow. And then I have also just given a little bit of a sense of day 3 when we come back in plenary and we'll hear the report out from the breakouts. And then we'll have a synthesis discussion from Ted and Louise again to wrap up. So I want to thank everybody for your participation here. Thanks for this great kickoff on the state of the science for population estimates. And I am going to adjourn our meeting here and let everybody go to lunch and have great breakouts tomorrow, and see you soon.
Thank you very much, Julie.
Thank you.